Good morning, everyone. Yeah, you can hear me well. Yes, we will start the second part of the Observing Ice-Ocean Atmosphere Interaction, Changes and Effects on Interannual to Centennial Timescales. And I will lead this session on behalf of the committee of this convener group. And Ari Olsen could not come, so I will step in for him, and I'm Agneta Fransson from the Norwegian Polar Institute, so I will lead this session. So we have 7 really interesting talks this morning until 10:30, and then we will continue with the third part after coffee break. So so I will not talk more because you will listen to all these presentations. So I will just give the word to our keynote speaker. It's Guillaume Boutin. Sorry, my French. He's from the NERSC, University of Auckland, New Zealand. And he will talk about modeling the wave impact on sea ice dynamics in the Arctic. So yeah, the floor is yours.
So, good morning, everyone. Thank you for coming, for those who were able to come.
Sorry, did you put it on?
Yes.
Yeah.
Does it work? No, and then I can use this one, maybe? Okay. Does it work now? Should I just use the other one? Yeah, I don't know. Okay, oh, it works, yeah. So, good morning, everyone. I'm Guillaume Boutin from Nansen Center in Bergen. I'm going to talk to you about the marginal ice zone and the impact of waves and sea ice dynamics. I would like to first acknowledge my colleagues from the Nansen Center, Tim Williams, Einar Olasun, my collaborator from Auckland University, Brown University, Chris Horvath, as part of the SACIP project, and Pierre Rampal and Laurent Brodeau, who also are part of the SACIP project funded by the Schmidt Foundation to better understand the marginal ice zone in particular. So let's start with the marginal ice zone. You may have seen this picture already yesterday. So what is the marginal ice zone? This is a place where the ocean and the atmosphere interact together, and these interactions are modulated by the presence of sea ice. And what are the waves doing in this big picture? The waves are generated in the open ocean because sea ice attenuates the waves and prevents their formation, and they propagate in the marginal ice zone over tens to hundreds of kilometers, depending on their properties, mostly how big they are. And when they propagate, they break the sea ice. And this is maybe the most important interaction they have with the sea ice. Why? Because when the sea ice is being broken by the waves, it becomes more mobile. And when it becomes more mobile, it has a feedback on all these processes, the mixing, the eddies, the lateral melt, etc. Because suddenly, like, you have a big change in the sea ice dynamics. And so this interaction of breaking up is extremely important. This is what I would like you to keep in mind. The second thing that I would like to insist on, to highlight, is that there is a context in the Arctic. So here what you see is a trend in the onset of refreezing in autumn, and basically this refreezing is arriving later and later. And for instance, more than a month in about 30 years in the Beaufort Sea. And so that means that there is more and more space to generate bigger and longer waves that will penetrate further in the sea ice. At the same time, the sea ice is becoming thinner, so it's becoming more fragile, so more sensitive to the breakup. So the impact of waves is expected to grow. It's very basic, but it's expected to grow. So coming back to the marginal ice zone, the real one this time, not a diagram, we have here a satellite image of the marginal ice zone. Here you have the pack ice, like we have clear structure, clear flows, very visible. This pack ice is hard to deform. It's not very mobile because you have these big flows that interact together and they are extremely hard to move around. There will be no eddies. But in the marginal ice zone, you can see that the ice has been moved around by eddies mostly here, but also by the wind. And so there is, again, this change in mobility between the pack ice and the marginal horizon. And how do we represent this change in mobility in the models? We only assume that this is because it depends on the concentration. So the surface covered by the ice. So which ratio of the ocean surface is covered by the ice. So this is not something extremely physical. It is something practical. But if you were to use a high resolution model, for instance, and if you look here, this ice is very mobile, but it is very compact. So it should not have a high resistance to deformation. The reason it is mobile is because it is fragmented, and this information of fragmentation is missing in models, because there was before no information about the waves, because it was not necessarily mandatory to have good results because of the resolution that was coarse and for which the concentration assumption was working good enough. But now we are getting to the point where this assumption might become necessary, especially if you come to sea ice forecasting. So we wanted to try using state-of-the-art model that we developed at the Nansen Center to estimate what would be the impact on sea ice dynamics to account for the fragmentation due to waves. So how do we do that? First, I will go back to actually pack ice. So on the left, it's a model called NEXIM, coupled to NEMO, actually. So what you see is the sea ice concentration overlapping the sea surface temperature. And when I show a little movie, you will see that in this animation, there is a lot of openings in the pack. There are cracks. And these cracks are extremely challenging to obtain normally with a standard sea ice model at this resolution of 12 kilometers. So how do we obtain these cracks? Here, we have changed the rheology, so the way the sea ice behaves as a solid material. And what we use is a brittle rheology. And I'm really not going to enter into detail about what a brittle rheology is. My group is working on it. I am not the absolute expert in that. But what I would try to convey is the idea that in a brittle rheology, there is first a damage quantity, that is a qualitative quantity between 0 and 1, that represents the mechanical resistance to deformation at the subgrid scale of the sea ice. So basically, when the sea ice is fully damaged, we assume it is full of cracks, and this ice is easy to deform. And these cracks are generated by the wind. When the wind exerts a strong shear on the sea ice, the damage value increases, and this ice becomes damaged and more easy to deform. And this is how you initiate and propagate those cracks. In a standard rheology, when you don't have this damage value, you need to be able to resolve this stress that is happening under the grid scale or at very fine resolution. So you can maybe have cracks if you use a very high resolution, like around 2 kilometers, where these cracks are generated and then they propagate. But we don't need that because we have the damage that is a subgrid parameterization of this phenomenon. And so, coming back to the marginal horizon, I said that the mobility depends on the fragmentation. Here, this is kind of what we do, but to model pack ice physics. It has been primarily thought for pack ice physics. Now, the second part of a marginal horizon system must be the waves. I can give you a very crash course in wave modeling if you are not familiar with it. First, energy comes from the wind that you provide with your analysis, and you can account for the presence of sea ice, for which you need to provide the properties that control the attenuation, which are the thickness, the concentration, and the flow size. Okay, so if we want to couple, these properties are going to be provided by the sea ice model. And the originality of the model that we have is something I have actually developed during my PhD in Brest, in France, is to have a feedback on the attenuation due to the breakup. So basically, the wave arrive, and depending on their statistics and their wavelengths and their height, they can bend the sea ice. And when they bend the sea ice too much, the sea ice breaks. And so we can decide whether the ice is broken or not depending on the wave properties. We can compute which wavelength of the waves is gonna dominate this breakup, which will impact the flow size that will result from the breakup. And in exchange, this new flow size will have a feedback on the attenuation. In general, the more it is broken, the less the waves are attenuated by the sea ice. The less the sea ice attenuates the waves. So the two important information that you have to keep in mind is that the wave model decides whether breakup occurs or not, and it gives an information about the flow size that results from the breakup through the wave wavelengths that dominate the breakup, that we call lambda break. And this we send to the sea ice model. And the sea ice model deals with the flow size, and that will impact some properties like processes like the lateral melting. So now I want to study the dynamics, and for that I will use only two qualitative information. We are going to keep very simple because it's quite a complex thing. and adding complexity will not help. So if fragmentation occurs, which is decided in the wave model, what we will do is that we consider that the sea ice is fully damaged, so in NextSim. So if fragmentation occurs in wave retrieve, the waves are curved enough to bend the sea ice and to break it, then we increase the value of damage, so we reduce the resistance to deformation of the sea ice. And why do we put it to the maximum? It's because damage was initially thought for the wind, and that breaks up the ice, and the crack that propagate, or multiple cracks that propagate, and the waves that will break the ice at a subgrid scale into very small flows. So you will have a very high density of cracks. So it's like a catastrophic failure for the sea ice. Now, that was a theory. In practice, how does it look? So on the left, you have the wave height. On the right, you have the sea ice concentration. This is a result from the Couple model. It is a storm in October in 2015 in the Barents Sea. And the magenta line here, as you can see it, this is the limit between the broken ice and the pack ice not broken to the north. Okay? So I run the simulation. I have waves that arrive, and you can see that the extent over which the ice is broken increases. That's good. I mean, the storm propagates waves quite far, and this wave breaks the sea ice. Now you have a second storm, and it's moving, etc. I think this is just to give an idea of how it works. And the same event, but this time with different variables. Here we have the flow size, so the smaller it is, the more broken the ice is. And in the middle, you have the damage value. You see, it's very qualitative. It's going to be very high where the ice is broken because fragmentation increases it, and less high in the pack ice. And completely to the left, to my left at least, so to your right, you have the ice drift speed. So let's first look at the left panel. So the wave arrived, the flow size is reduced, and the damage is maximum where the ice is broken. And now if you look at the ice drift speed, you can see it is really enhanced in the area where the ice is broken. Okay? So the question, so sea ice in the marginalized zone where the ice is broken is more mobile. Now the question is, okay, we have taken into account the fragmentation, but is the ice more mobile in the marginalized zone because it is thinner and not compact, or is it because we have added this information through the damage of the fragmentation by the waves? So for that we run two simulations, one in which we account for the effect of waves, I call CPL damage, and one in which I do not account for this effect of the waves on the damage, that I call WRS for very dark reason. And if I do the difference in ice drift speed after the storm, for instance, I can see that there is a whole area here where the ice is clearly, definitely more mobile, up to 50% more mobile for the hours that follow the storm. And why is this narrowband only and not the rest? Well, it's because in this narrowband, my waves are breaking compact and thick ice. So where my ice is not broken, is not is already not very compact and not very thick, the model already does a good job of having a high mobility because this is how they initially work. But by taking into account the waves, I account for the change in mobility in the in the thick and compact ice that becomes broken. Okay, so this is the added information, and as I said, the increase is quite dramatic in the mobility. So the really important thing, if you want to predict how the ice edge is going to evolve after a storm, is to know where the waves are going to make a difference, whether the waves are going to be able to break compact and thick ice. This is really important. So that was the result of our study in 2021. So now I'm going to have like 3-4 minutes to discuss rapidly the consequences of that. So first, this extent over which the waves travel in the ice and whether they're able to break compact and thick ice really matters for the sea ice dynamics, and so we want to be sure that the model is able to capture that extent well. So how do we do that? Well, the model had been evaluated before against 2 case studies in the Beaufort Sea and in the Barents Sea, so it is not too bad, in my opinion. But we would like to extend this, and we have had a very nice presentation of what altimetry can potentially provide us as an information about the marginalized zone extent yesterday. And we already started something like this with ICET2. So here on the left, this is the result of another study. So in the magenta points, this is all the places where ICET2 in November 2019 has detected the presence of waves. according to the algorithm designed by Horvath et al. 2020. And if you look only at the Atlantic sector, you can see that these locations make a lot of sense. They are quite close to the ice position, and they kind of form a line that varies between like maybe 50 kilometers in the Greenland Sea to a much larger extent in the Barents Sea, which is consistent with what we know of where waves have an impact. And in green area, this is where the model sees the same extent of waves in ice. And so there is a pretty good agreement actually in the Atlantic sector. I've done that for like from November 2018 to May 2020, and I found that the agreement that the model was showing some skill at capturing the variability of the MIZ extent in the Barents Sea. Now in the Beaufort area, for instance, you have in November a lot of detected waves here, and maybe, but there could be waves created in leads. It could also be artifacts. There seems to be the algorithm that they use. I doubt it detects real waves, or at least maybe the threshold that of which with the detects waves may be varying a lot between here and here. So yeah, this I believe it's noise actually. So there is still some work to do, both on the modeling part and then in the observation part. So there is also, Metno is also releasing a lot of buoys with a cheap buoy program led by Jean Rabot, and yeah, this is really a nice opportunity to both calibrate the model and observations, remote sensing. And the second thing is that I mentioned in the beginning that the Arctic is changing and waves are an emerging phenomenon. And we would like to use the model to investigate the future, like what is going to happen when the ice has receded. The good news is I've been recently funded a project by the NFR, so the Norwegian Research Council, to forecast the wave impact in the future. So this is going to start next June. This is just 1 minute of advertisement. And we hope to create kind of a small mini climate model using boundary layer models to have conditions representing the future of the Arctic on this existing wave ice model to try to understand better what is going on in the next 50 years. And the last thing I wanted to mention, we're at Arctic Frontiers, but there is one place on Earth that is already sea ice surrounded by the ocean, and this is the Southern Ocean. And this is the best place to investigate maybe wave ice interactions, because there you definitely have a lot of events where the waves propagate into very compact ice, and so will affect the mobility of sea ice. And this, the fact that models do not take that into account may explain a lot why they are terrible at capturing the extreme changes in sea ice extent that can occur in Antarctica, because physics of the sea ice in Antarctica is different. So I will just finish my talk, 16 minutes, perfect. So under small animation, so this is Antarctic sea ice modeled with NextSim. This is quite new actually. And the waves around, they are very high, up to 6 meters. And the green line is the ice edge. And you can see that they move a lot. You have a lot of storm, and they propagate very far. If I remove the ice to see how far they propagate, up to 500 kilometers. Some waves, some storm have been shown to be detected after 1,000 kilometers. So you have one place on Earth where waves and ice interactions really matter. And we can learn a lot about the Arctic with Antarctica, about the future of the Arctic, I think. So I'll leave you with a summary, and thank you very much for your attention.
Thank you so much for these very interesting talks about the waves propagating in the sea ice, and we are really looking forward to actually know more in the future in your new project. So it will be very exciting. So do you have any questions? Yeah.
Thank you for. Okay. Thank you for interesting talk. And I have one question. So how can we relate the damage of sea ice with observable physical quantities?
Oh, that's what we were supposed to do in the SACEP project, and it's complicated. We would like to link it to the flow size, obviously, because there seems to be a link, and the flow size is basically the density of cracks. And then you have, we were thinking of using DEM to try to see how the flow size impacts a bit the resistance to deformation, and maybe the transition from the regime where you have pack ice to the marginalized zone is really complex. And so yeah, what we are trying right now is using DEM to interfere with the physics of what happens in the marginalized zone, and then to find a nice and fancy way to determine when there is a transition between the two regimes.
So before the initial breakup occurs, so we don't know how the ice is damaged.
Yes.
I mean the 100% concentration.
In a 100% concentration, well, if your ice is really compact, we have the model is tuned to have in pack ice the right deformation statistics, so the leads, the ridges, the convergence, the shear, etc. So this can be relatively well constrained. So in that sense, you can tune the model rheological parameter to get the right deformation physics with a scale invariance that is really typical of the pack ice regime. Where it becomes really tricky, I think it is what happens to damage when you enter the marginalized zone, because then you have much less data to have information about how you should evolve this quantity. And here we took what is maybe a upper limit, like assuming that there is no resistance to deformation in the marginalized zone when it's broken by the waves. In reality, there will be flow-flow interactions, but the resistance will be much less than in pack ice still when it's not damaged. So we are capturing that. But the question is also, second question is, how do you heal the damage, I think, in this. Yeah.
Okay, so other than the flow size, etc., so do you have any suggestion for observational people to measure the quantity damage of ice?
How do we measure the damage? Yeah. No, it's always the same. Like damage is something that emerges from the model. It comes from geology, and the observation we use are always like the deformation, like the lead distribution, or the RGPS data to look at the convergence, divergence. We can also use, we can imagine that we can get information about the convergence using the roughness, etc. So this is all these more classical parameters that tells us whether our damage range is good or not. And you clearly see a scale of the damage between some values and some values, for which you get very nice features and very nice information. And if you get out of this range, suddenly the quality of your model drops. So there is something that you can constrain, for sure. But how do you link exactly what is the damage to one quantity or two? It is more complicated. Yeah, it is. I am not a specialist for that.
Yeah, thank you. That's what we
Yeah.
Okay. Yeah. So one more question. Anyone? Okay. Thank you so much, Guillaume. A very nice presentation. And so we can give you a applause. So now to the next speaker is Manuel Benzi. And he's from the National Institute of Oceanography and Applied Geophysics in Italy, and also National Research Council of Italy, Institute of Polar Sciences. So maybe you will give your title yourself, and you will talk about Svalbard.
Is the microphone working? No?
And the deep water there, and also
Is it working now? Yeah.
Yeah, it's better. Yeah, okay, thank you.
Let's wait for the slides. So good morning, thank you for the introduction, and I will speak about weak signs of dense water cascading from the Storfjordsen that we saw in 2020 in a phase of a long phase of Arctic Atlantification phase. So we move from the modeling part to the in situ observational part. So you are all aware about the phenomena that is named Atlantification, that is the increasing flow of warmer and saltier water from the North Atlantic to the Arctic Ocean. If you look at this Hofmöller diagram that shows the temperature and the salinity versus latitude and longitude in the North Atlantic and subarctic areas, we can see the evolution of the Atlantification in this area. In particular, we can see that the Atlantification intensified after 2000 with a peak around 2010 and a decline after 2019. And we can also see that the signal of the Atlantic water, as you know, is confined in the easternmost sector of the Atlantic, North Atlantic and Greenland and Fram Strait. So there are several associated changes to the effect of the Atlantification, and among them we can remember the reduction of sea ice cover, the weakened stratification above the upper layer occupied by the Atlantic water, and the enhanced atmosphere-ocean interactions. We are now in the area of the southwest Svalbard, where we placed our mooring some years ago. I will show you later the configuration of our mooring. And we are in an area that is very complex, where very complex oceanographic processes occurs. We have several water masses flowing here: the Atlantic water in the upper layer, the Norwegian Sea deep water in the deeper part of the water column, and several interaction with the polar waters and dense shelf waters that are coming from the shelf and from the Storfjorden, that is the major fjords here in Svalbard. So the use of moorings is extremely useful to detect fast processes and complex processes that occurs in the ocean, and it's also very useful and very important to collect long-term signals in the ocean that otherwise we cannot detect by periodical classical oceanographic cruises. The evolution of our mooring is issued here. We started our observation in June 2014, and we put a great effort to continue our measurements until now. Our mooring is still in the water. This is the Aquatal configuration, and in the last 2 years, thanks to several collaborations, we also elongated and increased the number of instruments on our mooring line. So now we are able to catch also information in the intermediate part of the water column, where the Atlantic water has more influence. So while at the beginning we started our measurements in the deep part of the water column, and we were exactly interested in catch also signals of dense water outflow from the Storfjorden. So if we look at the overview of the time series of temperature and salinity at 1,000 meter depth here, so we saw since the beginning that we found a couple of interesting effects on our data. So the periodical intrusions of warmer and saltier water, especially during the winter season, and we basically didn't find any signal of dense water at our mooring position, at least coming from the Storfjorden or from the shelf. This happened until winter 2020, where you can see here, but you can see better here, a zoom on the winter 2020, when we finally found some signals of cold water here. And here 3 events that are related to the intrusions of dense water, probably from the shelves. And curiously, that here was the previous one, was the first one after many years in which the Storfjorden one was again entirely covered by sea ice in winter, and also the offshore area was reached by sea ice flows during, in this case, is an image from February. If we move on a zoom of the second event, and probably the major ones we found during that winter, we see that the event lasted a couple of days with a couple of events, so it was a very fast process, and we can see that the deeper 300 meter thick bottom layer were decreased their temperature, but only the sensor close to the bottom, 20 meters above the bottom, catches the very low temperature signal with the values as low as -1.2. If we have a look at the stick diagram of the currents here, we can also see that the currents were very strong, up to 40-45 centimeters per second, and they were characterized by rotational event. So a quick look to the meteorological conditions and to the sea ice condition gave an idea of what happened during that winter. If we use the meteorological data collected in Hornsund, we can see that in the last 10 years, that cover more or less the period of our moorings, the lowest temperature during the winter were reached exactly in the R, were reached exactly during the winter of 2020. and the major winds, the strongest wind, were from the east and northeast sectors. As far as the sea ice monthly time series index is concerned, we can see that we know the long-term sea ice decline that is well known, but there is also 2 points that I wanted to remark here in the last 10 years of data. We had the minimum, not in winter but in summer, in 2016, and also that the maximum of the last 10 years, actually I could say also the last 20 years of data, were reached in winter 2020 again. Another interesting aspect of the data we have collected at our mooring S1, southwest of Svalbard, are the data that were collected by the deepest sediment trap, always located at 1,000 meter depth. Here you can see the time series of the ice rafted debris signal, so the particulates that fall down from the ice flows passing over the mooring, and the total mass flux, that is the sum of the organic and inorganic particles that are detected by the sediment trap here. And you can see that starting from our June 2014, we had our maxima in the winter 2020 and also in the winter 2022. If you see the evolution every 2 years of the sea ice images in March, you can see also the relationship between the presence of ice in the fjords that was almost absent in the first part of the period of our measurements and became more present after 2020 until 2022. Another interesting aspect that is interesting to be mentioned is the presence of zooplankton accumulated in the sediment traps. I have to say that the sediment traps, the zooplankton that reach the sediment traps at 1,000 meter depth can reach there only if transported by internal oceanographic processes, strong internal oceanographic processes. Otherwise, it will not be present there. And the maximum of the accumulation of zooplankton in the traps were observed in summer, fall 2018 and fall 2019, that are probably related also to the end of the phase or longer phase of Atlantification that I have shown you in the first slide. So to wrap up our conclusion, and you can see here, we could say that the Atlantification intensified after 2000 with a peak in 2010 and a decline after 2019. That the reduced sea ice extensions is related to higher intrusion of Atlantic water during winter-summer season and to enhanced vertical mixing. The understanding of internal processes is possible only if we maintain we ensure continuous measurement in the ocean, also during the winter season. The West Svalbard offshore margin is characterized by very high variability. The winter of 2020 was characterized by more sea ice formation and associated dense water production in Storfjorden and on the shelf, and we saw from our moorings. In the 9 years of data, exactly only that winter offered the condition, probably the condition to catch dense water intrusions at depth larger than 1,000 meter depth in the Storfjorden. Otherwise, probably the dense water will remain at the intermediate layer. And a delayed effect of the increased Atlantic water ingression is observed also at our moorings by looking at the abundance of the zooplankton accumulated in the sediment trap at the mooring site. Thanks for the attention.
Thank you so much. Very interesting
and
impressive time series you have there. So yeah, so you have a time for a quick question to Benzi. Manuel. Yeah, anyone? Okay, then we go for the next speaker. So
thank you.
So thank you.
Thank you.
So it's Laura Distur that we from the Norwegian Polar Institute. Also will talk about time series in the Fram Strait.
Yes.
In the outflow water. So yeah, when you're ready, please go ahead.
Thanks, Agneta. Yeah, good morning, everyone. Thanks for coming. I'm going to talk about ocean as well, but we're going a little bit higher in the water column to the surface, upper ocean, and sea ice properties in the Fram Strait. I shouldn't touch this, I should touch this. Arctic Outflow Observatory in Fram Strait, that's run by the Norwegian Polar Institute. And we're going to look at some changes and drivers in the last decades that we've observed there. Co-authors acknowledged here. I forgot Lars Hendrik, apologies for that. He has also been involved in the last paper that came out. So why do we study the East Greenland Current in the Fram Strait? I use this sketch here to show the Atlantic meridional overturning circulation. And you see the Fram Strait with the yellow bar is basically the bottleneck of this overturning circulation. This distributes the warm water at the surface throughout the ocean to the north, and then circulates back to deeper waters as a cold flow to the south again. And this is very important for our the climate as we have it in Western Europe. As you see, if we move to the Arctic then, this is a slide of Hiroshi's work of sea ice motion vectors in the Arctic Ocean. And as you see, the Fram Strait really collects a lot of this sea ice that's exported from the Fram Strait. And as well, underneath the sea ice, we have the surface circulation that's quite similar to this, where a lot of fresh water resides in the Arctic Ocean. And that also comes out through Fram Strait, not just through Fram Strait, but also a large part through the Canadian archipelago. But to monitor this export of sea ice and fresh water, and as well Atlantic returning water through the Fram Strait, all of these are components to this AMOC circulation. There's been this observing system deployed already since 1990, the first moorings, but more intense since 1997. And the western part of Fram Strait is then monitored by the Norwegian Polar Institute with these moorings, where we go every year and we survey this area and we collect moorings and collect the data. I'll be focusing on the upper ocean mostly in this talk. Yes, and we first start with some results that you maybe have seen already yesterday in Hiroshi Sumata's presentation. This is a unique time series of sea ice thickness collected in the Fram Strait. I think it's the longest record of its kind in the Arctic, or in the world for that matter. And you see that really in the first part of the period, sea ice thicknesses were very thick. And sorry, this is not sea ice thickness, this is sea ice volume export. The volume of ice exported through the Fram Strait. And this reached a record low in 2018 because of very weak velocities, so a very small southward export, as well as sea ice thicknesses. And then we go to sea ice thickness, here we see basically a regime shift in the sea ice from before 2007 and after 2007, where typical more thick ice and more deformed ice has now become more thin ice and more uniform. And the bottom figure here shows this shift as well, where the thickest, the fraction of very thick ice has basically been reduced a lot since 2007. Now, if we go to the ocean, the changes in sea ice is not only seen here in the sea ice, but also reflected in the oceanography. The upper ocean temperature record here of the polar water, so the uppermost water mass in the Fram Strait, coming from the Arctic, you see basically the seasonal cycle of the ocean temperature has increased, with increasing temperatures in the summer, especially since 2000 or after 2012. And this is monitored on the shelf, whereas if we go, this is then a seasonal cycle where we clearly see this increase in the seasonality with not just increasing temperatures, summer and late summer, but also an extent of this warmer period. So the season is getting longer with warm temperatures, making it more difficult again to grow sea ice. Then if we look at a different mooring in the same array, where we cover the deeper East Greenland Current, we actually see this process of, Atlantification also in the Fram Strait happening, especially in 2015. This is the occurrence of Atlantic water, and since 2015 we saw really a jump into the presence of Atlantic water in the East Greenland Current. So the East Greenland Current basically moved slightly westward. And then if we look at that seasonal cycle, the colors in red there show the most recent years, where you see that this happened mostly in winter time, actually this presence of more warm water in the strait. Now, both these temperature changes in the ocean had effect on the downstream sea ice concentration. That's shown here, where we do correlation maps of the ocean temperature with sea ice concentration downstream with different lags. So you see, for example, August, October, December, so 0 month, 2 months, or 4 months lag relative to the ocean temperature maximum in Fram Strait. We see that there's downstream, there's a reduction of sea ice concentration. Similarly, for the ocean temperature of the Atlantic water, if we correlate that with downstream sea ice concentrations, we see that this also has an impact on the sea ice concentration in winter. And both cases shown that there could be as much as a 30% anomaly or reduction. Now, a little bit on the freshwater, because this is one of the other important parameters we derive from this array. Here we see freshwater transport anomalies. So we don't show the full time series here, but this is deseasoned, and then we look at anomalies relative to the long-term mean. And we try to identify what are really the drivers behind these anomalies. And first of all, well, there's no clear trend. We haven't seen a big increase in freshwater as we would expect. Actually, the opposite. Because of this Atlantification in Fram Strait, we saw a reduction in the freshwater transport after 2015, so negative anomalies in the freshwater transport. And if we look at processes, PhD student just defended this, we actually see he could identify 3 different processes, and one has to do with, well, all of them had to do with sea level pressure variations over the Arctic in different areas. So we look at locally Fram Strait, upstream North Pole, or upstream Beaufort Gyre. And he could identify 3 different mechanisms. The top one, where we see North Pole convergence prior to a freshwater transport event, Beaufort Gyre weakening, for example, and these occur on different timescales from 1 to 2 years before an anomaly, as well as Fram Strait northerly winds, and that's a local effect where on monthly timescales the northerly winds cause a direct freshwater increase in the strait. Then a little bit about a comparison with modeling observations. A large part of the freshwater in the Arctic Ocean comes from the Pacific, so that's something we call Pacific water. And this you see on the right here, this panel, this is from a model simulation, how this Pacific water can be distributed in the Arctic Ocean. So it comes from through the Bering Strait, distributes over the Chukchi Plateau and into the Beaufort Gyre, and occasionally it comes out through Fram Strait. And this is we can measure this with nutrients derived fractions of Pacific water. Here you see observations from the Fram Strait, very impressive long record, and we see events where this Pacific water in red is very large or very weak in blue, and this model was really able to simulate this really well. And it was actually found that also here sea level pressure is very dominating driver, and we can now predict when this Pacific water anomaly would occur into the Fram Strait or not with an 11-year time lag. So these were just a few highlights of what we've been able to achieve last years, not all presented now, no time for that. Basically, the sea ice volume export reached a record low in 2018. Sea ice thicknesses have shifted from thick and deformed to thin and uniform ice. Temperature of polar water has increased typically in summer. Presence of Atlantic water increased typically in winter. And both of these effects have had impact on sea ice downstream. And then we've shown a little bit of some processes we were able to identify which cause Pacific water anomalies and freshwater anomalies in the straits. Now, there's no time to talk about everything, but there's going to be another talk after the coffee break by Melissa Cerecci, and it's going to deal about ocean acidification. So that was it. I hope I managed in time. Thanks.
Yeah, thank you, Laura, for a very interesting talk. And I wonder if anyone has a question to Laura. Very silent. Yeah.
Do we know what drives the sudden increase in Atlantic water in 2015? Why 2015?
Good question. So it looked like it was mostly coming from the central Nordic seas, not so much, well, in addition to the Manuel, yeah, you probably have seen this also in your mooring. So the West Spitsbergen current had also more Atlantic water, warmer and saltier. But in this case, specifically, I looked at sea surface temperatures then, and it showed that it was more in the central Fram Strait, more so than in the West Spitsbergen currents. And yeah, so it looks like there was an upstream mechanism driving this in the Nordic Seas, and I haven't gone into detail to analyze that. But I think also an important aspect is that the East Greenland current became weaker, so and occupies a smaller area, so that also allowed this Atlantic water to spread further west, basically.
So do you think that, thank you. So do you think that this could be spread further west, this Atlantic water up on the
I
shelf?
think, well, what we see now in more recent data, not shown here, but it showed also that in 2020 we see more a return of the stronger East Greenland current and more polar water again in the Fram Strait. So these are obviously periods that this is happening at. But generally, the impact of more Atlantic water on the thinning sea ice will be bigger because the sea ice is less and thinner.
Yeah. And another quick, do you have a quick question? Another? Okay, then we continue. Thank you, Laura. We'll continue with the next speaker. And that's Zoe Koenig, and she should be recorded. And the questions will be answered by, I don't know how to remember who. Okay, yeah, you're a biologist, but anyway, we can see afterwards if there are any questions. So, okay, so the presentation by Zoe, is it on? We can start.
But I'm actually on fieldwork right now. So Hi everyone, thanks a lot for letting me the opportunity to record this presentation. And first I would like to apologize for not being here, but I'm actually on fieldwork right now. So I'm presenting this work that is on turbulent fluxes at the ice-ocean interface in the Arctic Ocean. And it's a work done within the BRIS project in collaboration with the University of Calgary, the Norwegian Polar Institute, and the University in Tromsø. As you may know, the Arctic Ocean is one of the quieter oceans, mainly because there is ice that prevents any exchanges between, or reduces most of the exchanges between the atmosphere and the ocean. But although it's a quiet ocean, we still have some dynamics happening in the Arctic. And if we look at what's happening just under the sea ice, we have ice-ocean shear, but also some wind that can enter through leads, and that tends to create some mixing, which leads to some deepening of the mix layer, but also some mixing of the surface ocean. And this mixing has some strong influence for the biology. If we look at sea ice algae that grows in the ice, they still need nutrients, but this source of nutrients is actually the ocean. So we need some mixing to bring these nutrients all the way into the ice for the sea ice algae to grow. And on the other side, the sea ice algae also produces oxygen or CO2 depending on the situation, and that is also creating gradients that create fluxes in the ocean. So in this presentation, I will address the question: what are the dissolved oxygen and nutrient vertical fluxes at the ice-ocean interface, and in which proportion are they driven by the physics and by the biology? So to measure vertical turbulence fluxes, we have quite a common tool, which is called the microstructure profiler, as shown in the picture here. And basically, by using the vertical gradients of the heat or the nutrient on the salt, we get access to the fluxes. And what we get from this parameter is this diffusivity coefficient K rho. However, the issue with this instrument is that it's not free-falling straight from the sea ice. Indeed, it needs to be free-falling, and we can't have this data just under the sea ice. And also, these equations that we show here are not applicable in the boundary layer, so at the really, let's say, 20 centimeters just under the sea ice. So in this study, we use another tool, which is called an eddy covariance system. Showed here, it's composed of an ADV, that measure currents in a small parcel of water, and then associated to it we have a microscope that has fast sensors of temperature and conductivity and oxygen. By multiplying the small variation in the vertical velocities with the small variation in any quantity, which heat, salt, oxygen, like velocities, we get access to actually the vertical fluxes. And that's the equation I'm showing here. And in the rest of the talk, I will apply this convention, which is positive fluxes are from the ocean towards the sea ice, and negative fluxes are from the ice to the ocean. We want to look at nutrient fluxes, but as you can see here, we don't have nutrient sensor on this instrument. So we used a discrete approach to do that, using the water sampling, which is the nutrient fluxes are basically the friction velocities that we get from the ADV, multiplying by the difference of nutrient concentration in the far field side and at the ice-ocean interface. And we use this alpha, which is an interface salt or nutrient exchange coefficient that has been empirically estimated by McPhee and is estimated to be 8.6 to the power minus 5 in melting season. So the data we used in this study are data from the Central Arctic Ocean, and we used two sites, which are the Nansen Basin and the Amundsen Basin in August 22. And at these two sites we deployed the eddy covariance system and took water sampling, and the ice station lasted from about 36 to 48 hours. I'm going to show here data mainly focusing on the Amundsen Basin data set, but we get similar results from the Nansen Basin. What we can see here is that if we look at the time series in the Amundsen Basin, we can definitely see that the ocean is relatively warm at minus 1.3 and is not at the freezing point. The Amundsen Basin is relatively fresh for the Arctic, about 30.2 PSU, but that is expected. This is known that the Amundsen is relatively fresh. If we look at the currents, they are relatively slow at the ice-ocean interface on the order of 0.5 centimeter per second. And we can clearly see at the beginning of the time series the impact of the hole with a long adjustment time that we can see in these variables. We then computed the fluxes using the methodology as showed before, and what we can see is that if we look first at the heat flux, that is the third panel, we can see that the heat fluxes are positive, which indicates sea ice melt, which makes sense, we were in August there. On the other hand, salt fluxes are relatively negative at the beginning because we have the release of brine channel in the hole, and then they equilibrate around zero when we are in a more stable situation. There is almost no nitrate fluxes. That's what I've shown here on the fourth panel in orange. And it's actually, surprisingly enough, they are negative, meaning that there might be remineralization in the sea ice. If you look at the oxygen fluxes, which are the first panel, they tend to vary with a daily cycle. But what we know is that the oxygen fluxes are also affected by the sea ice melt and brine channel release. So we first had to remove this influence by assuming the amount of fluxes that are generated by the release of salt in our experiment. And what I'm not going to show it here, but once we've done this this computation and we remove the influence of the salt in the oxygen fluxes, we get actually we can then put them over 24 hours and compare them with actually the shortwave radiation that we get from satellite images. So it's the blue line are the shortwave radiation and the red line are the oxygen fluxes. And we can see that they tend to be in antiphase, meaning that what we can see that when there is light, we have positive fluxes of oxygen and it's a net heterotrophic regime. And what we see is that when there is even more light, so when we are in daytime, fluxes are close to zero or negative, which indicates an autotrophic regime. and that has to be linked with the primary production, and it's still under investigation. Last part of my presentation concerns the nutrient fluxes in the two basins. So I'm showing here data from both the Amundsen Basin in orange and Nansen Basin in green in the upper 25 meters of the water column. And we computed these nutrient fluxes using the microstructure profilers that we also used during this study. And I also added the two dots here in panel E that are basically the surface fluxes estimated using the methodology shown before. What we can see is that the upper water layer is very different in both basins, with something very much fresher and actually warmer in the Amundsen Basin compared to the Nansen Basin. The nutrients are also different in both Amundsen and Nansen, with much more nutrients in the Nansen Basin, while they are almost zero in the Amundsen Basin. If we look now at the fluxes in nutrients, which is panel E, they are much larger in the Nansen Basin than in the Amundsen Basin, but all in all, they are very low and even lower at the ice-ocean interface. And if we want to compare that, is that in the Barents Sea at the polar front, we get fluxes of an order of magnitude extra at the NutriClean. So just to give you an idea of the order of magnitude we get. So to conclude, the eddy covariance system is a powerful tool but tricky to work with. Oxygen fluxes at the ice-ocean interface are driven by both the biology with the diurnal cycle and the sea ice melt. Nutrient fluxes at the ice-ocean interface in the Arctic Ocean are very low, and this work is still under investigation, and the next step would be to link with the sea ice algae growth, in situ light, and primary production in the sea ice. Thanks a lot.
Thank you to Zoe for this interesting talk about what's happening under the sea ice. Yeah, so do you have any questions to Zoe, or that will be answered over there? Okay, if you don't have any questions, we can continue to the next speaker, and that is Ramiro Saural. Yeah, do you want this one? Or you go for this one, okay. And yeah, you from
Barcelona.
Yeah, Barcelona Supercomputing Center. Very exciting. So, yeah, okay. So the floor is yours.
Thank you. Good morning. My name is Ramiro. I am not an oceanographist either. I'm a meteorologist, and I've been working with Francisco Douglas Reyes basically on the ongoing drought over the Mediterranean, over the Western Mediterranean, over basically southern and eastern Spain, who have been suffering from a severe drought in the last 2 to 3 years. And we got in touch with a group at the University of Exeter working on polar climate and how the polar, let's say, the reduction in sea ice is affecting or shaping the atmosphere or the climate in general. And we have been linking potentially this sea ice depletion with this ongoing drought over southern and eastern Spain. So basically, for those who might be not familiar, we are dealing with this polar amplification, which means that the reduction, let's say, the increase in global temperature has led to a reduction in sea ice, of course, and this reduction in sea ice has, let's say, increased locally the amount of heating or warming over the polar cap much above the global average. So let's say that when the sea ice is reduced, there is, of course, let's say, an area which is previously covered in sea ice is replaced by water. This, of course, leads to a change in the fluxes, in latent and sensible heat fluxes, let's say, communicating the ocean with the overlying atmosphere. And this has, in part, explained how locally this, let's say, fact of decreasing the sea ice has led to a warmer pattern over the Arctic itself. This has, let's say, from my point of view, which I'm from the atmosphere, has led to basically a shift in the location, the latitude of the shed. We call as in the ocean, we have, of course, a jet in the atmosphere, and this upper level jet, basically this is the bottom panel for DJF in winter. The jet is basically centered around 40 degrees north. When you perform simulations, I will show you in a couple of minutes, you find, of course, an impact of this polar amplification, of this, let's say, excess of warming over the polar cap on the strength and the location of the upper level jet. This is just observations. So you will see in the bottom panel here is the DJF pattern of the zonal winds at around, let's say, 10 kilometers high in the atmosphere. And this is the trends that have been observed in the period from 1991 to 2020. So as you can see, this, let's say, largest warming, this is the trend in 2-meter temperature, the largest trends observed basically in winter over, let's say, 80 to 90 degrees north, has led to a change in the position and the intensity of the jet. You can see here positive variations in the strength of these zonal winds, and further north here, negative variations. So this is suggesting that the jet has indeed changed or moved southward from its position along this 1991-2020 period. And you can see here, this is also for observations or reanalysis, is ERA 5. You can see here that this has led to an impact on something that here we in the atmosphere are very, let's say, concerned about, that are cut-off lows. These cut-off lows are like low-pressure systems, but are not present necessarily at the surface. They're basically centered at the middle and upper levels of the atmosphere. And they are very important because they account for a large fraction of the precipitation over most of the Western Mediterranean, and also over, for example, Italy, southern Italy, parts of Greece, parts of Turkey, over much of the Mediterranean. Over some parts of the Mediterranean, these cutoff lows are also associated with a surface cyclone. So you have not only an impact on precipitation, but also on surface winds. But basically, over the western part of the Mediterranean, there are mostly no associated surface cyclone. So the main impact of these cutoff lows are on triggering precipitation events, which can be really intense and really heavy over parts of Spain, Portugal, and southern France. So here is the climatology of these cutoff lows. We have, for example, in these parts of the Mediterranean, about 20 to 25 events per year of cutoff lows. And these are the trends observed in these kind of systems. So as you can see, in ERA 5, there have been negative trends over this part, which is linked in part to this shape or to this change in the location of the jet. You have more intense westerly winds, and this leads to a, let's say, reduced likelihood of generating these cutoff lows. And here you can see the correlation between cutoff lows frequency or, let's say, formation and precipitation over the Mediterranean basin. You can see here that these correlations are significant and positive over most, let's say, a large part of eastern Spain, the far southern part of France, also over parts of central Spain, southern Italy, and also over parts of eastern, let's say, the Eastern Europe in some sense, perhaps the parts of the Balkans. So this, let's say, shows that if there are any changes in the frequency or intensity of cutoff lows, then precipitation over these parts could be affected. And indeed, we, with the people from the University of Exeter, who have been looking at this set of experiments, these PAMIP experiments are basically a dedicated set of experiments of atmospheric-only runs, first from observed sea ice around the year 2000. And then from, let's say, a future scenario around 2030 to 2040 with, of course, reduced sea ice. And by, let's say, comparing the future versus the past condition, you can observe, or you can find, which is the impact on, for example, the atmosphere or cutoff flows coming from this change in sea ice alone. There is no change in ocean circulation, nothing else, just a reduction in sea ice. So you can see here, this is the climatology from in present-day conditions in the year 2000 of this PMIP experiment. So you can see that the pattern is quite similar to that derived from the ERA 5. And this is the, let's say, the change in future minus present-day conditions associated coming merely from a reduction in sea ice over the Arctic. So you can see here that the pattern of change is negative and is quite in the same area as we found from the, let's say, the observed trends in observations and in reanalysis, I would say. So this is the same pattern as before, but showing the correlations between the precipitation and cutoff flows in the, let's say, a PMIP set of experiments. So here we can see that the change in the let's say, if you isolate, you just only take the effect of reducing sea ice, you will find a pattern which is quite similar to the one found from, let's say, in the observations or in the analysis, which of course are a result of a lot of different things together, acting together. And this is, as to complement, the changes in this PMIP experiment in extreme precipitation events. So this is the change in, for example, the 90th percentile of daily precipitation and the 99th percentile of daily precipitation for the 4 seasons. So you can see that, for example, here in spring or in fall, you see that this PMIP runs just from reducing sea ice concentrations over the Arctic are showing a reduction in the magnitude or in the, let's say, in the amount of precipitation falling only in the, let's say, more intense events of rainfall. So this suggests that, of course, that this is just, let's say, an isolated contribution from sea ice alone. Of course, as I said before, there are lots of different things acting together. But just from the fact that sea ice is reduced and will be reduced in the future under global warming, there would be, let's say, first, a less frequency of cutoff flows over the western part of the Mediterranean, and also a reduction in the intensity of extreme events, which in part could be potentially culprit of the ongoing conditions of drought over parts of southern eastern Spain and also other parts of the western Mediterranean. So just the take-home message would be that sea ice melt is already affecting the distribution of precipitation over southern Europe, basically over southwestern Europe, and will likely continue to do so in the next few decades. So, thank you.
Thank you so much for a very interesting talk. Do you have any questions? Yeah? Yeah? Yeah. You were first? Yeah? Please go ahead.
Thank you, Ramiro.
Yeah.
I'm wondering if there are, or if you found any thresholds in the sea ice reduction that can trigger this reduction of cutoff events.
These PMIP runs are just, let's say, a black or white scenario in which the 2000 conditions are the observed ones, and then in the future conditions, which are around 2030, 2035, according to the scenarios, is basically a reduction of around 10 to 15%, and of course over the sea ice edge, I would say. So it's just a fixed reduction. It does have a seasonal cycle of reduction, but it doesn't have, let's say, different possibilities of reducing 5%, 10%, 15%. No, just a single scenario with this fixed amount of reduction.
Yeah, just a quick.
And how do you get rid of the sea ice then? Is it an atmosphere-only model, and you just take out the sea ice?
Yeah, you just modify the boundary conditions for the atmosphere, and you just take, let's say, sea ice scenario resulting from a global mean warming of 2 degrees. So under a global warming of 2 degrees, you get the associated amount of sea ice, and you superimpose these sea ice conditions, reduced sea ice conditions, on the, let's say, on the model. So for the atmospheric model, it's just a lower boundary condition. It's just a reduction. As you could be able, for example, to change also SSTs. I don't know. We're just.
And it's one model. It's not an ensemble.
No, it's an ensemble of these are an ensemble of 7 different models. Yep, from 7 different centers.
It's a stationary result. So I mean, there's a lot of years, and you've just shown the average.
You have, these simulations are, each model has 100 ensemble members, so it's quite a lot of, you can compute the spread in the solutions and so on. So this is just the ensemble mean. Yeah.
Okay, thank you. I just wanted also to ask you, will it be less precipitation here in Tromsø?
Well, in Tromsø, according to these scenarios, over this part of the, let's say, around 65 to 70 north, there would be a reduction in the westerlies. So potentially there could be less frequency of these cyclones, these hurricane-like conditions.
Yeah. Okay, good. Thank you very much, Ramiro. Yeah, thanks. Yeah, I would also say that we will also, if you stay, all the speakers stay after for a little bit for coffee, and if people have questions, we can continue on coffee break. So, yeah, okay. So the next speaker, let's see. Yeah, did I didn't. Did I miss that? I don't know, but I think it's first. Actually, it's Heidi. Yeah, we're a little bit late. Sorry, we have to be quick. Okay, yeah. So the next speaker will be Heidi Yang from the Department of Earth System Sciences in Tsinghua University in China. Yeah, I think you can. Yeah. Okay. Let's go ahead.
Okay. Hello. Can you hear me? It's work, yes. So hello, it's my honor to be here to deliver this presentation, and today I'm talking about the relationship between the winter Arctic sea ice and summer precipitation in China. And first, I want to start with the research background. And we have known that in recent decades, the Arctic sea ice is declining, and it will have some impacts on the mid-latitude climate and weather. And for example, in the future, the extreme cold events in East Asia will increase, and the sea ice also can cause the an anomalous rainfall pattern in China, and the heat weather and the wildfire. And among all this influence, I want to strengthen the precipitation influence, especially the summer rainfall, because the locations, the rainfall in China has highly related to the East Asia summer monsoon, and we should be paying attention to the two important systems. One is the cold air from the north, and another is the Western Pacific subtropical high. These two systems conformed with each other and decided the intensity and the locations of the rain belts in China, and it's really important. So I raise the question is how Arctic sea ice can affect the rainfall in China, especially the summer rainfalls. The time span of our research is from 1979 to 2023, and the data and method are shown in these slides. And for the results, firstly, I want to figure out the conditions of the Arctic sea ice. And this picture shows the climatology and the variability of the Arctic sea ice from 1979 to 2023. It shows that the transition regions between the sea ice and the open seas change rapidly, and the Barents and Karen Sea, which locked in the red box, shows the larger sea ice variability. So we want to further research the change of the Barents and Karen Sea ice. So the time series shows that in all seasons, it shows a decreasing trend, and the scope is relatively higher in autumn and winter. So we are mainly focused on the winter Barents and Karen Sea ice, and want to research how it may affect China's rainfalls in the following months. So we do the lag correlations between the winter Barents Karen Sea ice and the rainfall in summer in the following months, we found that from January to May, although in some months there shows relatively strong signals, but it cannot maintain into the next month. But in June, we can see a deeper rainfall pattern, which means when sea ice increase in the Barents and current sea ice, there will be more rainfalls over the Yangtze River Valley in China, which we are locked in the red box, and less rainfall were in the South China, which are boxed in the red, in the green. And this rainfall pattern will be weakened in the July. We can see these pictures, and will be gradually diminished in the following months. And to further verify this deeper rainfall pattern, so we compare the correlated rainfall fields with the non-detrended data and the detrend data, and we found that the pattern and the intensity of the signals is quite similar and close. And also we see the time series of the detrended sea ice and precipitations. We found that they correspond well, especially after the 1998. So we find maybe the relationship between the sea ice and the rainfalls are more manifested to the interannual oscillations. And because the intervals of the sea ice and the rainfalls is nearly 6 months, it's quite long. So we think we need something to connect these two systems, right? And we guess it's the snow covers in the North Hemisphere. So what we do is to locate the key time and key period and key regions of the snow depths. So we respectively do the lag and late correlations between the sea ice and the snow depths, and the snow depths with the June precipitations in Yangtze River Valley in China, and we can find that the March show. So we first look at the lag correlation coefficients between the winter sea ice and the snow depth in the following months. We can find that the signals was contained well from the winter to the March, and it's soon weakened in the following months. And for the late correlated snow depth field, we can see that the strongest field appears in March. So combine these two conclusions, we think that the Northern Eurasia snow cover in March may store the signals from the sea ice and will release in the following months to affect the circulation and the rainfall pattern in China. Yes. So, and its content to process. One is how the Arctic sea ice affect the snow cover. So we give the correlated geopotential height at 500 millibar. We can see that there shows a low over the Northern Eurasia, and it enlarged and moved eastward into the following months and corresponds to the geopotential high and 850 millibar. We can see the most part of the Eurasia was controlled by an anomalous low, and northwesterly, it can bring the cold moisture from the ocean to the land. So for the precipitation and temperature in Eurasia, it will be more rainfall and lower temperature, and these wetter and colder conditions are helpful to the snowfalls in the winter and March. And we next check the snow water equivalent anomalies, and we can see in this high sea ice years, there are more snow water equivalent appears in the western Siberia, and in the North Sea ice years, there are less snow over the Eurasia. So we use the conclusions of the high sea ice years to minus that in the low sea ice years, and we found the difference field. We can see that when sea ice increase, there are more snow over the Eurasia, and we also checked the different fields in the following months. We found that although the snow contained in the April, but it soon be decreasing in May, and in June the signal is weakened and diminished. So we may think the main snowfall period is from January to March, and in May the snow melts very quickly. And it also can have an impact on the thermal and moisture conditions in the locally, and we can see the different anomalous to meter temperature fields. And for the soil moisture, we can find that drier pattern in May and a wetter pattern in July. And also for the vertical circulation, it has some change, and this change may affect the downstream circulation and finally affect the China precipitations. And lastly, I want to show the anomalous circulation in June, also within the in high sea ice years from both the 500 millibars and 850 millibars. Their anomalous low covers over the eastern Siberia and over Japan, and the location is quite near to the locations of the Western Pacific subtropical high. It have an anomalous weak high over there, and in the low sea ice years, in the over near the Baiko, the Lake Baiko, we can see anomalous high control there. So the difference fields shows that when sea ice increase in over the eastern Siberia, they are mainly controlled by an anomalous low, while the Western Pacific tropical high is relatively stronger and more farther north, and it's beneficial to the cold air from the north move southward and meet the warm moisture outside the tropical high. Yes, and it was more likely to make the Yanhua River Valley more rainfall. And the correlated field also shows that the anomalous southwesterlies converge with the anomalous northerlies, which brings more rainfall to the Yanhua River Valley. And because of the time limitation, this is the summary of the research results. And I think the mechanism of the snowmelt needs to be further discussed. And that's the end of my speech. Thank you for listening.
Okay, thank you very much for very interesting and how what's happening in the Arctic actually reaches farther south or farther east to China. So we don't have much time, but if you have a really quick question, we can take it now. Okay, if we can take it, we can take it after in coffee break. So okay, thank you very much. And so now we go into the last presentation here, and that's Simon Woods from what was it? Real Ice, yeah, UK. So yeah, please go ahead for the last talk.
Thank you. I'll try and keep us all on time. Hello, I'm Simon Woods. I'm not a scientist, and I feel very privileged to be here amongst you all. But I'm an entrepreneur, and I've been involved in a number of startups over the years, and Real Ice is Real Ice is a response to this question. Can we do anything about all the melt that we've all been talking about? David Attenborough, Sir David King, a number of, many people actually have asked this question. And the idea of if we could refreeze the Arctic, could we buy ourselves more time to deal with the CO2 and methane problem? And we saw that as a challenge. So there was a small team out of Bangor University 3-4 years ago that started looking at a paper written by Stephen Dash and Hilary Hartnett out of Arizona State University back in 2017 that was published in Nature. And it proposed a solution of 1 million, Americans call them buoys, floating in the Arctic with windmills on them. And that these would float around the Arctic Ocean, and they would produce power which would be used to pump water onto the surface of the sea ice, and that would thicken the sea ice. It was costed at something between $500 billion and $13 trillion, so not very realistic. But things have moved on a little since then, and the question, is this worth doing? And I don't need to tell this audience that the global impact of losing sea ice, or a blue ocean event in the Arctic Ocean, which is coming, and some predictions put that at 2030, others later. The global impact is significant. Sir David King, chief scientific officer of the UK government, talks about Vietnam being underwater if there's a blue ocean event in the Arctic Ocean. I was losing all of the rice from Vietnam, causing famine in East Asia. So there are really good reasons to look at this potentially, and not just to dismiss it as geoengineering. It's too big a problem, we shouldn't think about it. And of course there are local reasons to do this too. There are communities in the Arctic that need the ice, that exist. You know, their societies run on the ice, quite literally. We were about to do some testing at the Cambridge High Arctic Research Station in Cambridge Bay in November, but we had to delay. There was no sea ice. It was 2 months late this year, as you all know. And so local communities don't necessarily just want to sit back and say it's just going to disappear. It's going to get worse every year. And so there is some science, that there's some ideas out there, there's some papers been written, some modelling been done that we've based our work on. In particular, work done out of University of Washington by Cecilia Bitz on an idea of washing the surface of the ice at the beginning of the season, washing the snow off, or effectively creating slush out of the snow that's sitting on top of the ice, increase the conductivity, and encourage the natural process of ice growth from below at the beginning of the season, and then at the end of the season produce snow and insulate the ice that's been created, the new ice that's been created. And that's actually what we've honed in on, is that work, and we're working closely with Professor Bitz and the team at University of Washington to operationalize this paper. This is what we think a solution might look like. We are right at the beginning of this testing. We have a 5-year time horizon. We're in our second winter. The team just got back from CHARS this weekend, just gone. We haven't sorted out the energy side at all yet. We know that we are a demand center for renewable energy in the Arctic. We think we're the first people to ever ship hydrogen up to Cambridge Bay, up to the Arctic, and use it in an operational test like this. We built our own hydrogen-powered water pump and then shipped the hydrogen up there and ran our testing on that. But the eventual solution, as we discovered, and it was reinforced over the last couple of weeks, the eventual solution can't be dealing with the surface level temperatures and conditions. We were out in gale force winds in minus 46 degrees centigrade. Our guides didn't want to go out in the weather. There are too many variables. And so our idea is that we will have hydrogen-powered underwater vehicles which will melt their way through the ice, measuring whether or not new ice needs to be created in that area, or if not, withdrawing and moving on to the next, in a highly autonomous solution. We are not doing this alone. We've been selected by Cambridge University's Climate Repair Group as their ice thickening partner. So we're working closely with them. We are working closely with local Arctic companies as well. Smart Ice, for instance, are doing our measurements. They're Inuit-owned business that specializes in measuring ice thickness. And the idea is to base as much of this initiative in the Arctic in partnership with Arctic entities as possible, and not just to be fly-ins who just dump our technology on people. So the idea, as I mentioned earlier, is that we wash the snow at the beginning of the season, heading south, and then we create snow heading north at the end of the season. We've costed this at a very, very rough initial costing. and obviously as we spend more time on this, we'll develop this. But we think that we will have to operate on about 1 million square kilometers of sea ice every year, which is a quarter of the sea ice that's left at the end of the summer. And we'll operate on the areas where it's almost at the point where it could be multi-year, and a little bit of extra energy injection in the form of new sea ice would help it to last through the summer. And we think we can get that down to a cost of $10,000 per square kilometer, which in heat equivalent, I know this is not a CO2 system, so it's not a CO2 direct comparison, but in heat equivalent, because of the increased albedo, that turns out to be a very cost-efficient equation. So in order for us to stay on time, I'm going to finish there. But thank you for your attention. Thank you.
Yeah, thank you very much. Very interesting, exciting, and very challenging too. Yeah. So, do you have a quick question or a question? Yeah, we still have. Yeah, we don't have any minutes left, but if you have one question, we could take that.
Okay. My name is Edson from the Nancy Institute in Bergen. Just one question. There is a strong interest in expanding fisheries and shipping in the Arctic region. Do you see any possible future problem if you presented this work like you want to grow the sea ice that would be more or less opposed to some interest that we have now?
Yeah, absolutely. It's not the Arctic is not one place. You're right, of course. And our first test was in Nome in Alaska last winter, and there are some parts of the community that have new opportunities as a result of there being less sea ice, and so it depends where you are. But this is a directed solution. We only need to produce sea ice where we place the machinery, and so we don't. Northern Passage is another area where there could be good reasons to leave the melt as it is, but it's a directed solution. We put it where it's wanted.
Thank you very much for this talk. Yes, we just found out that we have a question here for Laura. If you have time to stay for that.
Is this working? Okay. We have an online question asking if what's the correlation between sea ice concentration, temperature, and surface temperature over average certain layer from 0.5 or to 100 meters, for instance.
Maybe he or she can email me.
Yes. The question is from Laura Castro de la Guardia, that she'll be following us at. Okay. Okay, great.
Okay, thank you very much, and thank you all speakers, and for this interesting session, and for all questions from the audience. And so now there's a coffee break, and I hope to see everyone here and all the speakers for the next session. Starts at 11 o'clock. So welcome back, everyone.
why we've got this discussion. It's biomimicry. We wouldn't call it gene editing like so we want to ended up doing quite late because of the travel, it's very complicated by the late arrival of the ice. There's more precipitation. So allow a certain amount of snowfall. The snowfall then reduces the growth of sea ice. So we wash that, put water on top, from below the ice, and then that slush hardens, and it just shows that we created 40 centimeters of snow in 3 days. No, it will move. It will move. So it will move south. It will move south at the beginning of the winter. So it starts in the cold and it may never get as far south as Nome in Alaska. It's too warm now. But in areas where there's a meter of ice, if you can increase that to 1 meter 30, 1 meter 40, it will survive the summer. So that's where we're focusing initially. And if you do that, that's a geographically large area. But if you do that, then you can increase albedo quite significantly.
That's a important thing is that they damage the speed. But normally they have to be damaged. Basically every time the ice rolls,
Oh no, at the end of the winter, we will add snow. So you go back to these regions and you insulate the ice that you've created. You're exactly right. So you do both. But there's more information on our website. If you look up Realize there's lots of information about the technology and also the science and latent heat issue. But this is good, isn't it?
Yes.
But what people think about is because we can't just accept this.
Basically, when the values of damage really reach like 0.9, there's kind of impact. Exactly like Nobita is a scaling equation with exponential minus capacity times expression. So it's basically the same idea, but this time based on the past event, like how much time you have been on the shifter. This is only this information. So that gives you an idea that we are having a higher resolution on the liquid scale. There's actually a place where there's a local information that is really big that is not captured at scale. This information as we can put more cells. Along this line, at the same way, you are allowed to reach here and such like this. Yeah, exactly. This is why it is the best way to understand it. It's a way to present what can be resolved at the scale of the organization. Resolve the information at some scale. So if we are running the scale of 2 km where this fine localization of it, because this is supposed to represent the very fine structure with the grid cell. So it propagates elastic waves. So you will lose the fact that it's extremely localized. Yeah, thank you very much. Okay. I think it's better to show it, because when you show, you understand better, but when you explain, so I'm not the mastermind behind it. So.
det är ingen pointer på det? Jo, det är pointer. Visa. Okej, och sen så där flyttar du fram och där flyttar du tillbaka slicen. Så det är väldigt, den kan du ha i fickan kanske. Så att den är på vart här eller någonstans. Kan inte ha den. Så här, nej det kan jag inte. Kan man så? Bra, kanske. Men det blir bra. Okej, ja men det blir spännande. Nu går vi ifrån. Ja, bra.
Okay, everyone, we're starting up again. Please take your seats. Thank you. There's a microphone. Okay, we have a last part of our session now, starting up. Please take your seats and pay attention. I actually don't have so much to talk about now, so I'd like to give the floor to the speakers. We have a little bit of time left at the end of our session, so I'd like the speakers to keep to time, please. But if it happens to be so, we do have a little bit of extra time at the end of the session for more discussion and questions. Okay, so first of all, we start with keynote speaker Melissa Cerecci from the Institute of Marine Research here in Tromsø, and she's going to talk about the chemistry in the Arctic outflow of the Fremstrait observing system. Thanks, go ahead.
Thank you very much, Laura, and I'm very happy to be here. And I also want to acknowledge my collaborators on this work, Agneta Fransson, Mats Granskog, Laura de Stour, and Paul Dodd from Norwegian Polar Institute, and also Colin Stedman from the Denmark Technical University. So all of you have heard a lot about the physical environment that is changing in the ocean, both warming and sea ice loss, and wave action is increasing. But we also see more and more evidence that the chemistry of the ocean is changing as well. And that is caused by that the ocean has done us a great favor by taking up about 1/3 of the anthropogenic CO2 in the atmosphere. So, and this has been, otherwise it would be even warmer in the atmosphere. But this has happened at a very fast rate. So meaning that the CO2 system in the ocean has changed and shifted to a less basic state or acidified. The ocean is not acid, but it's less basic. So these drawings here, or the figures here, shows how the consequence of this uptake, and that the pH has decreased in the seawater. And this shows the global mean surface pH annual decrease. And the plot below shows the atmospheric increase at the Mauna Loa, and then the corresponding increase of PCO2 in the surface water, this blue line, and also the consequent that the pH was decreasing. So the number is very terrible to communicate to an audience. It's 0.0016, or it can also be called sometimes 16 millipH, which I'm not really fond of either. It doesn't sound a lot. But in total, from pre-industrial times, pH has actually decreased by 30% in the surface ocean. So it's quite substantial. This has also led to another term, which is tricky to explain, the aragonite saturation. And aragonite is a form of calcium carbonate, which organisms are producing. And aragonite saturation has decreased due to this acidification, meaning that you get a higher dissolution potential in the ocean. So a dead shell will dissolve quicker when you have low aragonite saturation. For organisms, it means that it needs more energy to create and form skeleton and shells. And this is also one of these acidification indicators that we are, in a way, using when we report how the ocean is changing. Acidification is not only calcification. There's lots of other biological consequences, changes more in the internal functions of the organisms. And you can also have something like changes in behavior. What is less studied and less known is the effect of acidification on other pH-sensitive processes. This is an example where, for example, the strength of how metals bind to organic matter or biofilms or microplastics, and which affects in a way the release of, for example, trace metals that are bioessentials. So the release or limit on these trace metals for the organisms. It can also affect the release and form of heavy metals, and also in a way affect the toxicity of some of the heavy metals, for example, mercury. And of course, we want the ocean to continue to take up and sort out our mess that we produce in the atmosphere. So we need to continue to follow what's going on in the ocean's role in this uptake on the global carbon cycle. So we also know that there are big changes. This polar amplification that we see evidence of is that we have been thinking that it will probably also enhance acidification. And this map shows the surface water aragonite saturation. So the lower value here means that you have a higher dissolution potential of calcium carbonate. So maybe more energy demanding for organisms to create. And so the surface water of the Arctic has naturally low aragonite, and that is because it has, in a way, high CO2 coming from lots of accumulated CO2 from remineralization of organic matter on the shelves. And this water from these shelf seas are transported in the transpolar drift current and then also enters the East Greenland current, which Laura described a lot about, and bringing this water then further downstream. Acidification, we start to see also acidification in the Arctic Ocean. This is from the Amerasian part, or the Western Arctic, and this blue blob here is evolution of a corrosive water, which you can see also extends, it's below 1, and it extends further north, but it also shoals. So you have more, it coming further up to the surface water. We also see acidification going on in the Amundsen and Nansen basins, where this shows from 100 meters to the bottom, doing repeat sections from 2005, 2011, 2015. And this red, the more red color you see means that you have accumulated more and more anthropogenic CO2 in this water column. You can see that this CO2 is accumulated between 100 and 1,000 or 1,500 meters. That's where you have the maximum concentrations. What is also interesting to see is that the deep water is older, so it has not, does not contain any anthropogenic CO2. What we also recently discovered in the Nansen Legacy project was that the Barents Sea, that the PCO2 in the surface water in the Barents Sea is increasing at least twice as fast as the atmospheric increase. So, and that also was in areas, occurred in areas connected to where we saw the largest sea ice loss. So it's probably related to that as well. So the main questions is, can we detect this ocean acidification that we see occurring in the Arctic? And can we see it in the Arctic outflow waters in the Fram Strait? And if we do, what rates? And what can be the main drivers of this acidification? Is it only the atmospheric CO2 increase, or is it something else? And also if we can detect influence from the Eurasian shelves and the transpolar drift, and also perhaps we can see if sea ice loss and freshening is affecting acidification. So we went to this extraordinary observatory in the Fram Strait, and we jumped on board the annual cruises that Norwegian Polar Institute has in August, September every year along 79 North, so going from Svalbard to the northeast Greenland shelf, and to in a way capture both the inflow water and the outflow water on the western side of the Fram Strait. And we then believe that we will, by sampling here, we believe that we can get an integrated signal of the change that occurs inside the Arctic. So we were sampling, we focused in the upper water column in 400 meter and sampling lots of acidification variables together with other like nutrients and freshwater tracers to in a way understand more on what's on the different drivers of the carbonate system. So you can see that this is just to show how the Fram Strait in a way captures both the inflow, the warm, relatively saline water from the Atlantic water close to Svalbard, and also this outflow water from the Arctic here, going in the East Greenland Current, but also on the shelf with cold water and lower salinity than the Atlantic water. We could also see that the Fram Strait also captures these contrasts in the chemistry, and this is also aragonite saturation, where on the Atlantic water side you have higher aragonite coming in, and then because the Atlantic water has a higher alkalinity. And then you see in this side, the western side near Greenland, you have the outflow waters and seeing the low aragonite saturation coming from the Arctic. So I will focus to show you some results from the East Greenland Current, because that's where we have the core outflow, Arctic outflow. And but we looked also in the shelf and in 3 different layers. We did a linear regression of all these variables between 2011 and 2019, and to see whether we could see any trends. So these are some results. Showing then in the upper 30 meters in this EGC area, the pH was decreasing about 4 times faster than the global mean. So this is the global mean, 17 millipH, maybe I get used to say that, compared to 78 millipH. So, but it's also visualized by this dashed line, which shows the global mean surface pH, and you can see that the rate of this in the EGC in upper 30 meters of the East Greenland Current, that we have much steeper decrease. Aragonite saturation was also decreasing by twice as fast as the global surface ocean on the mean rates of those. We were also then, as I mentioned, looking also further down the water column, where we in a way saw this enhanced or faster decreased rates also in the whole water column in the EGC, and it was a little bit different rates here, but in general it was faster than the global mean. We could also see that the PCO2 in the surface water, and it was also in the upper 150 meter, was about 5 microatmosphere per year, and you can compare this with the atmospheric CO2 increase rate of about 2 microatmosphere per year. So there is something going on that we cannot only explain the decrease by the anthropogenic CO2 increase or the atmospheric increase, but there's other processes that need to explain why we see this fast decrease in pH or fast increase in PCO2. So one obvious reason could be that we know from other studies is that fresh water is very efficient to dilute the basic ions, the buffering ions. And that means that you decrease alkalinity and also aragonite saturation very efficiently. So that in a way, the more fresh water you get, the more you enhance the acidification. This is just showing from our study in the Greenland fjord. This shows alkalinity versus then the amount of glacial meltwater, and then you see that the more meltwater you have, the lower alkalinity, and we see that also for sea ice meltwater and river water. And the Eurasian River, all the rivers surrounding the Arctic has increased river discharge, but in particular on the Eurasian side, where these large rivers draining from Himalaya have increased river discharge. So that could be a reason also explaining that the fresh water, the dilution of buffering ions. Sea ice loss that we talk about a lot also here shows that the blue areas during summer shows also the decreasing trend, where you see a large decrease in summer sea ice loss. And we also see this in some areas during winter, that the sea ice is disappearing or decreasing. So that means that we get more open water, and we have this cold, relatively fresh surface water, has a high solubility and high potential for uptake of CO2. and that could also, in a way, be a more efficient uptake of CO2 here. We made a study also when Agneta was out on this N-ice. We found that even after these storm events, which were in a way cracking up the ice, you got these leads and cracks, and then we could see on our measurements that we actually increased the uptake during these storm events in these cracks. So we were looking at the potential of uptake in these cracks, and it was very high. So then it goes back to that we have if we have more sea ice loss, we would then have more efficient CO2 uptake in openings, in more open areas. So to summarize, yes, we see progressing acidification at 3 to 4 times the global mean pH decrease rate, and the fastest was in the surface water in the East Greenland Current, transporting then from the Eurasian shelves. And the Fram Strait is a really, really great place to study this chemical change, not only the physical change, as Laura showed. And we think that this enhanced acidification is a combination of that we have both dilution of buffering ice through increased fresh water in the Arctic, but also that we have more open areas that can provide this efficient uptake from the atmosphere into an increasingly open ocean. So, and then this is a beautiful illustration from Frida showing, trying to illustrate this, that we have more open and you get a stronger push down into the ocean, decreasing pH even further. And then also if we look into the future a bit, is that continued, of course, climate change and warming may induce more permafrost melt on the Siberian shelves, and there's a lot of things going on there that can, in a way, increase the CO2, and then that will also enhance acidification. So it's important we continue with this study. Thank you very much. That's
Thank you, Melissa.
Thank you. Thank you.
Are there questions from the audience?
Thank you, Melissa. I have a question. What do you think about the relationship between the increased stratification of the upper layer in terms of carbon sequestration in the deep one? So do you have any evidence of some changes there or not yet?
Yeah, I think it's a bit... yeah, it's a good question. We're also wondering a bit about that. But of course, you have the sea ice formation, and the sea ice dynamics will increase with the increased seasonal ice cover. So that could, in a way, also enhance the pumping of CO2 further down. And that's what we think, in a way, explains why we see it throughout the water column. In the halocline layer, we also see this fast decrease in pH. And there are different reasons for the processes behind this decrease is a bit different in these different layers. That is why I have been working on this paper for too many years now, because I want to explain there are different things explaining in the different layers. Yeah. I think Pedro has a question.
Thank you, Mr. It was a very nice talk. I have this question. You showed these increases in the fluxes of CO2 from the atmosphere to the ocean. And as I understood, but correct me if I'm wrong, you emphasized the importance of, let's say, the physical state of the water, which is colder and therefore undersaturated. And so if you open the ice, you get more fluxes. And so the ocean is absorbing CO2. And I was wondering, do you have any idea about how much the biological processes contribute to create this CO2 deficit, especially taking into account that over the last decades there was apparently an increase in primary production?
Yes, so of course, as also Agneta showed yesterday, is that the dilution is diluting buffering ions, but biological primary production takes up CO2. So then you have phytoplankton taking care of the CO2. But then again, if you're looking on the full annual cycle and also how much that is actually sequestered, because otherwise it just comes up when you have at the end of the season, then it will come up again. So then it's the net effect that is important to see. So then you need, in a way, to push down the carbon, but so the biological carbon pump has to be more efficient. And that is difficult to know whether you have phytoplankton just increasing in the upper ocean, but it doesn't really transport it further below the euphotic zone, and then that's not the net effect is it's not a change. So and that will also rely on what type of phytoplankton you have, if they are big or smaller. So it's a tricky question. But of course, what is driving the seasonal uptake of CO2 is phytoplankton production mainly in the Arctic, so and in the subarctic as well.
Is it maybe an idea to put more instruments on the mooring array so that we can measure this year round?
Yes. Yes, I want that.
We need funding, I guess.
Yes, we need to do that better, but it's tricky, and it's tricky to get this thing off.
Thanks again for Melissa.
Yeah, thank you. Shouldn't we have earrings?
Oh.
You have similar earrings.
Yeah. Take off your earrings. Okay, we're ahead of time. I think that looks good. Next speaker, Lucie Goraguer. Unraveling phytoplankton seasonality in the northern Barents Sea. Please go ahead, and we have time, but not stick to the time.
I will try. Thank you for the introduction. So, hi everyone. I'm happy here today to present some first results that we have worked together with a large team effort of several colleagues from different institutions. So, this subject is about the seasonal dynamic of phytoplankton communities in the northern western Barents Sea. So, we have worked together under this Nansen Legacy project, which during the last several years we have conducting field work in the Barents Sea. Laboratory research and modeling studies. We have been focusing on the North Barents Sea and also the Arctic adjacent basin. So in this study, we are trying to see if there's any link between the phytoplankton biomass and communities in the Barents Sea with the environmental factors such as the sea ice and the inorganic content in the water column and the water masses. So to give a bit of a background of phytoplankton, so as we just talked about, phytoplankton at the base of the marine food web. So we have a nice illustration here from Frida. So if the phytoplankton are here, and we have many species that other species rely on. So the primary producer will be so the base for the entire Arctic food web, from the bottom to the apex predator that we have here in the Arctic system with the polar bear. So in this study, we have taken phytoplankton to water samples, and we have done taxonomy analysis under inverted microscope, and we have divided this phytoplankton into four major taxa. Sorry, we have the diatom, which are more autotroph species, so they produce from the CO2 atmospheric and the light, they produce the organic matter. We have the flagellate, which are more heterotrophic, mixotrophic, or autotroph species, as well for the dinoflagellate, and then we have the ciliate, which are more heterotrophic species. So the phytoplankton are an important major component of the marine carbon cycle. So here in the Arctic, we have a really strong seasonality in the vertical carbon export. So for example, in the winter when it's dark, the water is well mixed, there's not so much nutrient at the surface layer to let the phytoplankton growth happening. So we have a system that is more heterotrophic with more flagellate species, for example. Later in the season, when we have the light coming back, we have a more autotrophic component with diatom species. Centric are usually dominated over the pennet forms. So we have these Thalassocera species, which are typically spring bloom species in the Arctic. And later, when we have a late summer, for example, when we have reducing the light regime and less nutrient at the surface water layers for the phytoplankton to grow, we have a more heterotrophic system. So we can see that the seasonality of the phytoplankton community composition will impact, so therefore, this vertical export. And also, we just talked about the biological carbon pump. So the phytoplankton are really an important component of the biological carbon pump. By doing so, the sequestration of the CO2 atmospheric from the surface layer, where we have the light penetration into the water column, and that will bring this organic matter that is produced by the phytoplankton towards the bottom of the ocean. So therefore, if we have a change in these communities of phytoplankton, we will have also impact on this overall biological carbon pump. And so to do so, we studied the Barents Sea. So here you have the map of the Barents Sea region, and we can wonder why we study the Barents Sea. So the Barents Sea is a really high productive Arctic shelf sea, and is a hotspot for environmental change. So we observe that the Barents Sea is warming 5 to 7 times faster than the global average. Also, with this environmental challenge, that will have an impact and consequence of the structure and the functioning of the marine ecosystem. For example, here we will talk more about the phytoplankton community's composition. Few characteristics about the Barents Sea region. So the Barents Sea is a high seasonal variability. We observe a really high seasonal ice cover. For example, during the winter and the summer, the ice cover is really different, and then we have a difference in the water masses versus Atlantic versus Arctic water masses. So our sampling location starts from P1 to P7, which are the main stations. So in P1 it was Atlantic water influences, and then in P6 it was also Atlantic water influences station. And then we have the more like P2 to P5, the more like central Barents Sea station, which are more polar Arctic water influence. And then we have also a few stations in the Nansen Basin, other marginal Arctic basin. So I will start to look just at 2 seasonal cruises that we have been conducting. So during the same sampling time, we have August 2019 and August 2018. So we have done the same transect, and we can look first at the sea ice concentration. So we have a really high interannuality between 2019 and 18. So in 2019, we have a much reduced ice cover compared to 2018. So in 2018, we observe an earlier and more extensive sea ice retreat compared to 19, a warm Atlantic water inflow, more extended northward in 18 compared to 19. Also, the nutrient was deeper in 2018 than 2019. If we look a bit now at the phytoplankton biomass on the right panels, so we use the chlorophyll A as a proxy for phytoplankton biomass. So we integrate the chlorophyll A from 0 to 90 meters from the upper surface layer. And then we can see that in 2019 we have much more chlorophyll A than 2018. And if we look now at the phytoplankton composition, so we can see that overall in 2019 we have a higher contribution of autotrophic species, which are the diatom and the green here, compared to 2018, where we observe more ciliate or heterotroph species, the red colors here. So by looking at this phenology of phytoplankton community composition, we can say that 2019 was an earlier stage of the bloom compared to 2018, and that is so with the community's composition of phytoplankton. So we observe a higher contribution of small-size autotrophic species and more heterotrophic species in 2018. So 2019 was a late bloom stage compared to 2018 was more a post-bloom stage of phytoplankton composition. So now we can look at the 7 seasonal cruises that we have done in Barents Sea. So we have here the sea ice concentration. So we have done this sampling in March, May, July, August, and December. So in March we observed the larger sea ice extension in the Barents Sea that was reducing during spring and then becoming lower during July and the summer month, and then increasing again in the winter. If we look a bit at the biomass, we observed that in March we have a really, really low biomass of phytoplankton in the winter compared to spring in May, when we have a large increase of phytoplankton biomass. Also observed during July, and then we have further decrease towards the summer, end of the summer, and December to start to be really low again in the winter. If we look at the Atlantic influenced stations, so P1 and P6, especially in May 2021 during the spring boom, and also during July, we can see that we have a higher contribution of biomass of phytoplankton. So that means that this warm Atlantic influenced water is bringing more nutrients. Therefore, the phytoplankton bloom can start earlier during this station, Atlantic influenced station. If we look a bit at the species composition of this phytoplankton, we can see that in winter, in March, we have really low biomass of phytoplankton, but it's mostly dominated by dinoflagellate dominants, which are heterotroph, mixotroph species. And then in May, during the spring bloom, we have more autotroph species community composition. And also during July is more autotroph species. We've observed a lot of distal associated species during the spring bloom. And later in August, we have a decrease in the autotroph species composition. And we observe like increase of ciliate, so heterotroph species, mixotroph species with flagellate. And then in December, again, we observe a higher contribution of dinoflagellate species. So we can really see that the successional pattern of the phytoplankton community is starting from more heterotrophic, mixotrophic dominance towards autotroph species during the spring, summer, and then decreasing again with more mixotroph and heterotrophic species. So to conclude, we observe that if we have an earlier sea ice melt and longer open water period, like we have in August 2018, that will impact the timing and the successional pattern and overall community structure of the phytoplankton bloom and composition. So if we have more heterotrophic species and heterotrophic species, mixo and heterotroph, we will have impact on this biological carbon. Indeed, the species composition will be different, so the vertical export will be different. Species has different rate of sinking, so that will for sure impact this pump. To conclude on the seasonality, we observe that from March to May we have a really large increase of diatom species dominance. And then we can also see that the sea ice meltwater stratification and nutrient limitation will constrain the phytoplankton biomass during the summer. And we have a really low biomass in the winter with dominance of dinoflagellate species. So also, if we have a difference in timing, we observe a difference in timing of phytoplankton bloom between the Atlantic influence station, P1 and P6, where we have an earlier bloom compared to the other Arctic water influence station, a bit later bloom. This will have a consequence, for example, if we have this Atlantification of the Barents Sea, this will have a further consequence on the phytoplankton bloom. And it will be interesting to look at the autumn because we are missing a gap between August and December. So it will be really interesting to see if we have this autumnal bloom that has been observed. Yeah. Thank you.
Thank you very much, Lucy. Are there any questions?
Thank you, and I'm sorry if my question is not very precise, but if I understood well, there were lower values of phytoplankton in 2018, right?
There were what? Lower values?
Lower values of phytoplankton. So I'm wondering if there could be in some way related to a major presence of zooplankton that maybe hit the phytoplankton.
Yeah, that's possible. I haven't looked at this data, but yeah, there's a new paper now from colleagues looking at this also, yeah. But that's possible because they're grazing on them, then we have we will measure less phytoplankton in the water column. Yeah, less biomass if there's more grazer. Yeah.
Thank you.
More questions? If not, then we continue to the next speaker. Thanks again, Lucy. Thank you. And next speaker, Rosalie McKay. Welcome. Influence of contrasting turbulence regimes on sea ice microbial communities. We're still doing well on time, so we get to enjoy more biology. Thanks. Maybe have it upside down. Yeah. Okay. There we go.
Yeah, there we go. Careful. Yeah. Yes, that seems better. Just set the timer here.
Hi everyone, my name is Rosalie. I'm a third-year PhD student at UIT, and today I'm presenting a study that will comprise one of the chapters of my thesis. It's also a component of the Research Council of Norway funded project BREATHE. So this study takes us to the bottom of the sea ice, where algae and bacteria make up the base of the polar sea ice food webs. They tend to be concentrated in the bottom ice, and they represent an important concentrated food source, especially early in the spring, as the sea ice algal bloom happens before the pelagic bloom in the water. These algae are able to produce sugars and oxygen through the process of photosynthesis, and then also in the reverse reaction where they use these sugars and oxygen through the process of respiration. So the algae and bacteria are both doing this to grow their biomass. This results in conditions where we can have net autotrophy, where there is more photosynthesis occurring, or situations where there's net heterotrophy, and the reverse is happening, where we actually see more respiration. Because they tend to be concentrated in the bottom ice, this is where a lot of the studies will focus, because there's more biomass there. It's exciting to study that. However, this means that we have a gap of knowledge in what is happening in the middle and top sections in terms of the carbon balance within the ice and what this means for exchanges with the atmosphere and the ocean below. So for this study, there's different ways to estimate primary production, many which are based on carbon. For this study, I've used oxygen optodes, which uses a sensor into a bottle, which you can set up in a very similar way to carbon-based photosynthesis versus irradiance experiments. However, we're then measuring the change in oxygen over time. You can then convert this through calculations into milligrams of carbon equivalents through a quotient. Then you can get the gross primary production to produce your photosynthesis versus irradiance curves. One of the advantages of this method is because we're using oxygen, we can also measure negative changes in oxygen, which will give us estimates of heterotrophy, which is just not possible with some of the carbon methods. So onto the study site. It was in Arctic Canada. We worked out of the Canadian High Arctic Research Station, CHARS, in Cambridge Bay, and we selected two study sites, Poly 1 and R2, which were based on sub-ice turbulence. The theory of the hypothesis being that with increased turbulence, we would see increased nutrient delivery to the bottom of the ice, and this should result in differences in community structure for the microbial communities. So Poly 1 is our high turbulence site, where the strait is constricted through the Finlayson Islands, producing more turbulence under the ice, versus R2, which was a little bit protected in an embayment area. We targeted similar snow depths. This was a strategy to try to keep the light acclimation similar for the bottom ice algae between the two sites. So in a nice way, we did see some differences in the community structure. So these are flow cytometry results. So we have abundance in cells per milliliter on the y-axis versus the date that they were sampled on the bottom. So the high turbulence site, Poly 1, we see not only that there were at times even 5 times as much cellular abundance compared to the low turbulence site, but also that over time we saw a change in regime. So we saw an equal split of pico and nanoeukaryotes earlier in the study, and then nanoeukaryotes started to take over before what was kind of a community crash towards the end of the study, where either melt or kind of mass cell death occurred. So then throughout this low turbulence site, we saw little change in cell counts or the community structure between the two. I am currently working on microscope analysis to get idea on the microeukaryotes, so unfortunately I don't have that data to show here, but there was a study in 2018 in the same area that showed that over time the microeukaryotes and nanoeukaryotes took over in terms of ratio of these communities over time. So it'll be a nice comparison to see if we see a similar pattern with this study or if there's interannual variability between these sites. Not only were there differences in the cell counts, but also that we saw changes in the photophysiology. So these are photosynthesis measured in gross primary production versus light. Important aspects of these curves are the alpha, which is the slope of the line in the low light area of the curve, and that gives an indication of how well the algae are able to adapt during low light conditions, and Pmax, which is the maximum rate of photosynthesis possible. What we see at the high turbulence site, which are these top two plots, is that throughout the study period, both the alpha and the Pmax increased, versus the low turbulence site where there was not much change between the alpha and Pmax over the site. So what this is showing is that not only did we have this increased algal abundance at the high turbulence site, but also that they were better able to adapt to low light conditions over the course of the study and also have a higher maximum rate of photosynthesis. Onto nutrients, these are showing nitrate values in micromoles per liter on the y-axis. This is the low turbulence site R2, where they were just very low for the entire study. What's really interesting here is that at the end of the study where we saw that crash in the algal community, we see a spike in the nitrate concentration. So whether that is due to cellular release of stored nitrate or just that there was less algae taking up less of the nitrate at this point in the study, hopefully I'll be able to decipher that once I get all of the data. We were also able to collect intracellular nitrate by extraction with boiling millicue water. And what we see is, oops, too far, wrong one. Over the course of the study early on, that we saw an increase in the stored nitrate. What's important to notice here is that the concentrations are much higher. We had a maximum of just over 1 micromole when we looked at the intercellular, but intracellular was up to 20 at the highest point. This crash in the nitrate values at this high turbulence site doesn't match as well with the community crash with the pico and nanoeukaryotes. However, perhaps once I have the microeukaryote data available, which will contain much of the diatoms that we see in the bottom ice communities, perhaps we'll see a link there. So that'll be really interesting to see as I work through this data set. So on to bacterial abundances. So this is, again, flow cytometry results. So we have cellular abundance on the y-axis. Purple is our high turbulence site. So we see, again, there's this link with this crash, the community crash towards the end of the season, that the bacteria went up. One of the most interesting things, though, that I think is that even though we had much lower algae at the low turbulence site, throughout the study period, the bacteria is actually quite high. And since we normally consider sea ice bacteria to be associated with the algae, it's interesting that they had such high abundance even when the algae was not present. So then to kind of look a little bit more at this algal abundance versus the particulate organic carbon, used chlorophyll A as a proxy for the algal abundance on the y-axis here. This one is the POC, so particulate carbon. We see a very similar pattern at this high turbulence site between the two. However, when we look at the POC, the value is quite high considering that the chlorophyll is so low here. So there seems to be some sort of decoupling between the chlorophyll and the POC happening. So I then plotted the POC versus chlorophyll to see if there was a linear correlation, which at the high turbulence site we see very well, whereas at the low turbulence site, again, just seems to be decoupled from this algal amount. So then looking more at the POC at both sites, we have collected from the bottom 5 centimeters, mid centimeter, and technical difficulties. My head's too small. Anyway, mid 5 centimeters, top 5 centimeters, we collected at the interface water was very low levels of POC, whereas we saw very high POC in the bottom ice, which is expected at the one site because we had so much more algae. However, at the low turbulence site, it's also very high. So again, just indicating that the bacteria perhaps have a lower efficiency food scale, but they're still important. So it's less efficient because bacteria is so much smaller. There's more predators, so there's more steps in your food web there. And then also measuring the mid and top sections that were enriched versus the interface water. I was also able to do some net community production incubations. These are showing results towards the end of the season, where in the high turbulence site we had net heterotrophy and net autotrophy actually in the low turbulence site, which is very interesting. Thank you. So what this means for the carbon balance in the sea ice, I'm not quite sure, so that remains to be seen. So to conclude, it's going to be really important to continue with these microscope analyses so that I can start to determine what are the most important components for multivariate statistics to see what is affecting these microalgal and microbacterial communities. And then also in summary, we did see differences in size and structures in the microbial community with these different turbulence regimes. Primary production did seem to vary with community structure. We saw some evidence that microalgae can act as nutrient storage in these systems. Some evidence as well of low efficiency bacterial food webs when the low algal production is present, and that still not really sure what's happening with microbial communities in the ice column, so it remains to be discovered, I guess. So thank you. That was just over time. Oh, sure.
Thank you very much. Despite the technical difficulties, keep it on for a while.
Yeah. Well, now
are there any
seems
questions? Discussion points?
Here all day.
Yeah, in the back there.
Thanks, Rosalie, for a very interesting talk. I have a question regarding the photophysiological adaptation.
Mm-hmm.
Your both sites, do you know anything about the time scale on how varying this turbulence is? So are they like entirely very turbulent and low turbulent? Because it's a little bit surprising to see the adaptations in the physiology.
Yeah.
On this scale.
So I've pulled out tide charts, which conveniently, because it's close to the CHARS research station, there are tide charts available, and it does vary quite a bit over the study period. How this relates, I'm not quite sure yet. So maybe with multivariate statistics, maybe I'll see that there is some correlation. I've only shown photophysiology from like one site at the beginning of the study and one site at the end. So we visited each site 7 times. So I have 14 PI curves for each one. So I don't have any comment to say on that quite yet because I haven't fully looked at the whole data set to see, but it is possible that there is a link, and it's possible that I have data to show something towards that. So thank you for your comment.
Thanks.
Hey, thanks, nice talk. Did you have a look at other nutrients and their role in the community dynamics like phosphate and silicate?
Yeah, we have phosphate and silicate. I just didn't show it here. So they were fairly low relative to even other studies in the area, so I'm not sure if that was just an interannual variability. And then with of course, I think because there's quite a few diatoms in this community, the silicate was quite high in terms of intracellular, and then low relative for like the bulk nutrients in the ice. But yeah, I do also have that data.
Thanks.
Yeah.
No more questions again? Okay, thanks again.
Thank you. So stuck now.
You're never going to get it off. Thank you.
Thank you.
Just take a little time to put it on carefully. Okay, thanks, Emily. Emily, welcome, Emily. Thanks, Rosalie. Emily Stidham coming up from University of Alaska Fairbanks. About 2 decades of observations of different types of species, namely pelagic tunacates and pelagic snails in the northern Gulf of Alaska. Please go ahead.
Thank you. Hello, everybody. As she said, I'm Emily Stidham. I'm a master's student, just recently defended, working with Dr. Russell Hopcroft in the Northern Gulf of Alaska LTR in Alaska. I'm very excited to talk to you about what I've been working on for the last few years. But before I get started, I just want to acknowledge that we do work on the ancestral unceded lands of the Dene and Sugpiat people, and I want to thank them for their continued stewardship of these lands. Now, who am I talking about when I'm talking about pelagic tunicates and pelagic snails? In the Northern Gulf of Alaska, for pelagic tunicates, we have larvaceans, pictured here, all pretty, as well as doliolids and salps. And as for pelagic snails, we're predominantly talking about our pteropods, which is the same species that you see up here in the Arctic, Limacina, Helicina. It's our favorite. They're what we call our thecazomes, or sea butterflies, and they're predominantly fed on by our gymnosomes, or our sea angels. And collectively, or before I get to that point, I'm predominantly going to be talking about the larvaceans and the pteropods, because they're the predominant biomass that we see in the Northern Gulf of Alaska. And together, these can all collectively be referred to as mucus net feeders. They love mucus, they use it to eat and feed, and I love mucus too. And that overall, these are a gelatinous and fragile group that are rather unrepresented in the literature and just talked about in general. Now, why do we care about these guys? Well, they're efficient grazers, particularly the larvaceans, that are able to short-circuit the microbial loop, meaning that they're able to feed on a much smaller size fraction of phytoplankton, and often preferentially will feed on pico and nanoplankton. Not only that, they're major producers of marine snow and will heavily contribute to our biological carbon pump through their fecal pellets, their houses. And when I say house, I mean if you see this larvation on the bottom, that beautiful mucosal filtering system it builds, then it will shed it every time it clogs or gets scared or just ready to finish feeding, as well as their shells and bodies as they fall down. We kind of demonstrated by this beautiful paper over here. They can also make up to 30% of community biomass, which is the second, and they compete as generally the second most predominant or abundant grazers globally compared to copepods and euphausids. So they're very heavily abundant. And not only that, they're important prey for important commercial fisheries and seabirds. So in the Gulf of Alaska, they heavily contribute to the survivability of pink salmon and also contribute to walleye pollock diets. Now, the Northern Gulf of Alaska system is a highly variable and seasonal system. So we have that large spring bloom like you see in the Arctic, except ours is in late April, early May. And then it kind of decreases during the summer. We even have a small bump again in the fall before we go into that kind of dead winter period when we have all these storms. Now, a strong part of that variability is due to the Alaska Current, kind of shown here from that splitting of our North Pacific Current. It's kind of where most of our physical variability from the salinity and things like that happens. But we also have strong atmospheric forcing that is happening in the Northern Gulf of Alaska. So first off, we have those strong winds that come in the winter and have these storms and make it a strong downwelling system. But in the summer, those weaken, and we even see some weak upwelling that happens in the summers. These winds also force all the clouds on the mountains that surround, so those black bars around the edge of the Gulf of Alaska there is the precipitation that we see, and it can even rival that of the Mississippi rivers in the Gulf of Alaska. And all of that precipitation means we have a strong freshwater influx, which pushes our Alaska coastal current in the brown there, which is a buoyancy-driven current that gets super strong along the coast going into summer and early fall. And of course, we also have kind of what's talked about in the North Pacific Gyre, our high nutrient, lower chlorophyll water, which influences our offshore system. And finally, we have this newer concern that's growing. So we have these marine heat waves that are happening. So in the Pacific, we had the blob heat wave, as we like to call it, from 2014 to 2016. That was a heat wave that extended to an El Nino. And then 2019, we had another heat wave. And these are expected to increase in duration, frequency, and intensity as global warming continues. And when I mention heat waves, you're going to see this little symbol pop up as we look at my data. So what did I do? Well, we did collections using this modified California vertical net. Oop, not yet. In the upper 100 meters of the water column along the Seward line right here, kind of out of Resurrection Bay between Prince William Sound, Kodiak Island. We have collections every May and September since 2001. I processed all of the samples from 2012 to 2021 from every odd station. So that was 240 samples I did, combined it to 370 samples total for a 20-year time series. And as I'm moving forward, when I'm I'll split some of this into sections. So when I talk about inshore, it's this section here, mid-shelf, oceanic, and our Prince William Sound stations. So let's take time out of it. Before we shove 20 years of data at you, let's break it down into just the seasons. So the patterns that we're kind of seeing, first of all, larvation community composition is highly seasonal. Our spring composition is predominantly made up of two species, our Oikopleura labradoriensis, as well as Fritillaria borealis, and it's pretty steady kind of across that shelf. But as we move into fall, we see our other species of Oikopleura, which seems more associated with our ACC, that fresh water that comes in and current that runs along the shelf there. And we also see higher diversity that starts to show up the more offshore you go. And our warm water taxa also predominantly show up at our oceanic stations with higher abundances in our autumn. Now we're looking at the series, this full-time series here, and don't get too overwhelmed. So I've broken it up here where the IMO is our inshore, mid-shelf, oceanic. We've got our percent larvation species composition here, and then we've got time. So this is spring, and like I said, you can see it's fairly consistent across the board, both between years and within the sections, the regions. And if we bring in fall, that's where things get a lot more interesting. So you see this light blue Oikopleura dioica showing up more inshore. And then we also see the more beautiful colors that show up more offshore from all our warm water taxa that'll show up. And if we zoom in here on our heat wave years, you'll notice that Oikopleura dioica, I guess I have this, shows up earlier in the year due to higher freshwater influx earlier in the year due to the warming. And we also see there's a lot more warm water taxa that are dominating the system. And the really interesting one is this yellow species here, Fritillaria fraudax. This is our first record of Fritillaria fraudax in the subarctic Pacific. And it shows up in our blob years, but it's also shown up in 2021. So we're still trying to figure a bit more, but it's really exciting to have this new record. We also decided to do some NMDS plots to kind of start looking at the community and compare it to some other variables. So kind of looking here, it's kind of the farther spread out they are, the less related they are to each other based on the years. And so you'll see kind of these clusterings of the cold years, especially in spring, are fairly closely related, and our warm years are more spread out. I'm going to add in here some sections. So blue here, this is our inshore species. You'll see they're very tightly clustered in spring and a little more spread out in fall, but they're still more tightly clustered, whereas our offshore is where a lot of that scatter happening and where a lot of our variability in the community is happening. And we also, this cool little section right here is our Prince William Sound species. And so they're very distinct and have their own community that's happening in the spring before it kind of gets more jumbled up in the autumn when we have more mixing between the sound and the rest of the line. We also did a distance linear based model here, and we compared it to a bunch of climate indices, including El Nino and the Pacific Decadal Oscillation, our temperature, chlorophyll, and salinity. And we found that 18% of variation in the community could be attributed to those factors in the spring, and 28% of that could be attributed to in the fall. So just some interesting kind of beginning to look at drivers of this community. Now, pteropods were a little more complicated. So same thing, we got our years along the bottom here. This represents the abundance. We've got our intro stations at the very top moving on to the bottom. And so if we look at our years here, it's hard to kind of start to pick out patterns. It's the closest thing we're going to look at here is the heat waves. It's still not entirely clear about how they're being affected by heat waves, but we do see that there's a decreased survivability between our spring and our fall. And we're not entirely sure why that's happening, but this summer sampling is a kind of a new, we've got about 3 years. Thank you. So then we decided to do some linear regression. So this is showing the linear regressions that actually prove significant of comparing it to the same sort of thing. So North Pacific gyre oscillation there, Pacific Decadal Oscillation, El Nino Southern Oscillation, compared it to our Limacina. And the interesting thing was in the springs, we see that the North Pacific gyre oscillation seems to have a fairly high influence compared to the other things that I've looked at, as in the PDO and ENSO had the strongest in the autumn. So that's suggesting that there's an advective quality to, or effective driver to this group that we previously hadn't really explored. And when we ran this, just the climate indices versus our groups, we found an R-squared of 0.4 for our Limacina in spring and 0.187 in the fall. Again, suggesting that there is a much more advective driver involved here that we might not previously explored. So very exciting. So some conclusions from all of this that I just threw at you right now. So there's cross-shelf gradients and strong seasonal signal in the community at the species level. We also had new species occurrence records for our previously underreported species, and even the greater subarctic Pacific. We had some connections that have started to be established now between our community composition, heat waves, and our decadal oscillations. And these kind of highly resolved time series like this will be crucial to understanding how these communities and their seasonal patterns are going to be altered in the changing ocean. As we know, they're changing rather quickly. And of course, can't do it without all the help that shows up. Just quickly mention the funding from the UAF Graduate School, the NSF, and the Norwegian Polar Institute that brought me here, and everyone that supported me through the last part of analysis on the cruise last year with the Norwegian Polar Institute. Thank you, everybody.
Thank you very much. Is there a short question for now? No? A long question? Okay, well, if there are more questions, we still have a little bit of time left at the end of the session.
Yeah, feel free to come find me.
Thank you very much. And then, next speaker, Bethan. Yeah, there you are. Okay, next speaker, Bethan Langley, University of Glasgow, on the Arctic and subarctic marine carbon storage and meta-analysis. Please go ahead.
Thank you very much. Yeah, so hello everybody. Today I'll be sharing some of my PhD research. It's on Arctic and subarctic marine sediment carbon storage. So, carbon, it's the building block of life, and it's constantly on the move around our planet, from the atmosphere to the ocean to land and living organisms and into marine sediments. And it's the carbon in these marine sediments that I'm particularly interested in. So marine sediments play a vital component of the global carbon cycle. Marine sediments are vast sinks of carbon, and they can store carbon for millions of years over geological timescales if they're undisturbed. Marine sediments also help to regulate climate, and they can be seen as a nature-based solution to mitigating climate change through the action of drawing carbon dioxide from the atmosphere into the ocean and then the burial in deep sea sediments. However, carbon in marine sediments is vulnerable to anthropogenic pressures. And as I'm sure many of you are aware, the Arctic is warming almost 4 times faster than global averages, which is causing catastrophic effects across the environment, including increases in sea surface temperature, declines in sea ice, increased precipitation, and increased runoff, all of which can affect the production, the delivery of carbon, and the preservation of carbon in marine sediments. Furthermore, anthropogenic activities such as deep sea mining or trawling can disturb sediments, promoting the remineralization of carbon in these sediments, consequently releasing carbon and potentially contributing to global carbon emissions. But despite this significance, importance, and their vulnerability, carbon stocks across the Arctic and subarctic are yet to be spatially mapped and quantified. Yeah, big question mark. So to address this knowledge gap, we asked the following research questions. How is organic carbon distributed across Arctic and subarctic marine sediments? How much carbon is stored in the top 1 meter of Arctic and subarctic sediments? And finally, what are the drivers of organic carbon distribution and what are the drivers of the hotspots of carbon? So to do this, moving on to our methods, we conducted a systematic literature and data search for marine sediment cores across the Arctic and subarctic from 50 degrees to 90 degrees. And we also looked for their organic carbon concentrations. So from this, we compiled a database of marine sediment cores, which we call the Arctic SED-OC database. And this figure here shows the distribution of sediment cores across the study site, just overlaying on a bathymetry map. So in our database, we have a total of 1,414 sediment cores, which makes it the largest database of sediment cores across the high latitudes. In the database, 794 of these cores have data readily available, and a further 620, they've been measured for organic carbon, but the data wasn't available. So here's just a little plea to all scientists to share their data after they published it. So there's pretty good distribution across the Arctic and subarctic. The mean distance between the cores was 33 kilometers. The highest number of cores came from the Arctic Ocean, 205 in the Arctic Ocean, followed by 203 in the Greenland Sea, and then a further 142 in the Baltic. More than half of the sediment cores were extracted from the continental shelf, followed by the abyss, and a much smaller amount in the Haddle. So, moving on to the carbon stocks, so the spatial mapping. So we use forest-based regression in ArcGIS to spatially predict organic carbon in the top 1 meter of sediment across the study site. And our model constructed 1,000 decision trees, and it included 21 biotic, environmental, and physical variables. And in the interest of time, I won't read them all out, but these include temperature, salinity, distance to glaciers, sediment porosity, all of which are known or hypothesized to influence the production or the preservation of carbon in marine sediments. To then convert organic carbon concentration into stock, we created a dry bulk density raster. This data came from Atwood et al. 2020. And I guess moving on to the results now. So this figure here shows the distribution of organic carbon in marine sediments across the Arctic and subarctic. This is at a 1 kilometer resolution. And we found that organic carbon ranged between 0.23% and 5.8%, and the mean organic carbon concentration across all pixels was 1.01%. We identified hotspots in the Baltic at 3.34%, the Kattegat and the Bristol Channel, and by identifying these regions of high organic carbon concentration, we can begin to consider where protection and management should be implemented to ensure the effective conservation of these areas. Okay, so just a little bit about the model performance. This figure here, we have measured organic carbon concentration on the x-axis and then predicted organic carbon concentration on the y-axis. And when we plot the data, so each grey dot indicates a sediment core in the model, we can see that there is good agreement between measured and predicted, with the data lining close to the dashed line, which represents the 1-to-1 ratio where measured equals predicted. Okay, so I guess this is like the big number that I'd like you to remember. So we found that 236.6 petagrams of carbon is stored in the top 1 meter of Arctic and subarctic sediments. Over half of this was stored in the continental shelf, so 56% was in the continental shelf, followed by 33% in the abyss. And when we spatially average this content, we find that per megagram, per hectare, we find 84.14 megagrams of carbon in Arctic and subarctic sediments. And then when we compare that to global averages from Atwood et al. 2020, this value is much higher compared to 66.56 megagrams per hectare. So this implies that Arctic and subarctic sediments are important carbon sinks, and they do play a large contribution to global marine sediment carbon stocks. So we also used the World Database on Protected Areas to work out how much of this carbon is protected, and we found that just 0.09% of this carbon currently resides in protected areas, which leaves a significant amount of carbon that is vulnerable to human pressures that could release this carbon back into the atmosphere. So just moving on to variable importance, so the drivers of carbon hotspots. On this figure, we have all the variables that we used in the model, and then the importance on the x-axis. And we ran the model 250 times so we can get a distribution of their importance. And we found that sediment porosity, sea surface chlorophyll, and sea surface salinity were the most important variables in driving these concentrations. So an important question might be to ask how future changes in these variables might influence carbon buried in sediments, because we do know that, for example, salinity and chlorophyll are changing in the Arctic. So just some takeaway points from this presentation. So firstly, Arctic and subarctic sediments do play a large contribution to global marine sediment carbon stocks, and they store 1.3 times more than global averages. Secondly, over half the carbon stock is stored in the continental shelf, with hotspots identified in the Baltic, the Kattegat and the Bristol Channel. And by identifying these regions of high carbon content, we've can begin to consider where management should be implemented to protect these regions. And finally, given that our key predictor variables are likely to change in the future, and that just 0.09% of carbon is currently protected, humans will likely play a large role in shaping the future carbon stocks in the Arctic. Thank you very much.
Really good talk. Thank you very much. Impressive work. A huge data set you have worked on. Are there any questions from the audience?
Yeah, thanks for this very nice talk. Philip Aspi, Norwegian Polar Institute. I was wondering, have you also looked at nutrients as a variable to determine your organic carbon content contribution in the sediments? Because I would think that the overall nutrient regime will probably say quite a bit about how much organic carbon we actually find in the sediments. And I didn't quite see it on the list of parameters you had, so whether it's something you could maybe also to consider and to include.
Yeah, thanks for that question. So in earlier iterations of the model, I did have nutrients included in the model, but because I had chlorophyll primary production in that model, I feel like they were better drivers to explain carbon concentrations. And also when I had the nutrients in the model, like it made no difference. It didn't improve the predictive power. Thanks.
Actually, similar question to our earlier one. I'm wondering, in some places of shelf, let's say Siberian shelf, you may expect that a high ion content in water will enhance sequestration of organic carbon. It could be also observed in other parts of the Arctic Ocean. Would it be possible to include this ion data in your database, or check at least if those sediments has this kind of data?
Yeah, another good question, thanks. So I did also have ion concentrations for the surface waters in the model to begin with, but then again decided to take them out because I had primary production and chlorophyll as variables themselves. But I do think actually if I could find data on ion content in the sediments, that could be quite useful information, because I know that, well, I believe that ion can affect the preservation of carbon in sediments, so that could be quite interesting to see. But no, there's no ion data that's currently in the database itself. It's just, well, it's organic carbon concentrations and nitrogen, and then some radiocarbon data, but that's a separate project.
Any other questions? No. Okay, well, thanks again. Thanks. All right, and then our last speaker of the session, please come to the stage. Jan Sverre Laberg, talking about the response of the northeast sector of the Greenland ice sheet to past climate warming. You were not going to use this one?
Well, I can give it.
You can? Yeah?
Yeah.
You have short hair, should be easy. Yeah. Behind the back, over the ears.
Like this?
Yeah.
Okay. Let's see if this works.
Yeah, thank you. And yeah, please go ahead.
Okay, thank you very much. And now you guys will have to rescale time-wise. I'm a geologist, and I will be talking about an evolution over thousands of years. And the focus here is on the northeastern sector of the Greenland ice sheet. And the study aims that I will discuss with you here today is, first of all, have the northeastern sector of the Greenland ice sheet always been of the same size as today? And if not, when did it reach its present size, and why? And in very short, how do we address these questions? What is the way that we are looking into this? Well, as geologists, we are looking at the seafloor landforms. What is the morphology of the present-day seafloor in this area? And then we do sediment coring to analyze the seafloor sediments, which represents the record of the past climate in this area. So to take you to the area that we are presently focused on, this is the East Greenland continental margin from Scoresby and up to Germania Land here up in the north. The present-day ice front is indicated by this red line that you see here. This part here is the continental shelf, and over here to your right you see the deep sea area of the Greenland basin. And in very short, I want to show you that during the last glacial maximum, the ice front advanced from here and all the way out to the shelf break. And the consequence of this is that the morphology of the present-day shelf of Greenland is a glacial influenced shelf. It's formed by grounded ice, meaning that it includes troughs and banks in this area, as we will see. The two areas that we have focused on so far in this project is the outer shelf in this area here, and then it's one fjord system, which is the Bessel Fjord that you can see over here. And I will quickly show you some bathymetry data from these two areas. And I don't expect you to pick up all the details, but I will try to explain to you what are we looking at here. We are looking at two parts of the sea floor on the continental shelf in this area here. And the colors relate to water depth, meaning that there is a scale bar here, and you can see that red and yellow colors are shallower and darker blue are deeper areas. And in addition to that, you can see that there are a number of lines both on this image here as well as on the image that you see here. And these are morainal ridges. They are formed during the retreat of the ice from the shelf in this area. And the ice had a number of stops and re-advances to form this type of signature. So we know this signature from other glaciated continental margins. Okay, the other area that we have been looking at is the Bessel Fjord, and here is the result of 2 seasons of bathymetric surveying that we have done in this area here. And in the lower panel, we have outlined the area, the deepest areas. This is because this is where the sediments that we are looking for, this is where they are located. But now I will show you a transect running from out here and along this fjord all the way to the inner part. How does this fjord really look like? And here is the here is the profile running from your right and all the way to your left over here. And as you can see in this fjord here, there is a very pronounced sill in the outer part. Here is the scale for your reference. There is a very pronounced sill in the outer part, and then you see as we move further in, it gets deeper in some areas, very deep, and you can also see that there are peaks in here. And our interpretation of these peaks is that they relate to the grounded ice stopping at these positions. It's also morainal ridges. And there is one interesting thing to be observed in this particular area is that we see these ridges in the fjord, but we don't see them onshore. Meaning that for some reason the dynamics of the ice when forming these were not directly linked with the ice that was located onshore. So this is the type of data that we are using in order to reconstruct the behavior of the ice sheet in this area. And in addition, which I don't have time to show you here, are sediment coring that we do in the first area that I showed you, but also in the fjord that you see here. Okay, so what is the result of all of this? What are we able to do based on this? Well, we are able to try to date the behavior of this part of the ice sheet. And now you see that we are considering the period from the last glacial maximum through a period called Younger Dryas, which is between 12,009 and 11,700. And then you see we have the situation like 11,000 years ago, 9,000, 7,001, and then in the late Holocene. And what you see indicated here is that these arrows indicate that the ice all along this segment of the northeast Greenland margin reached out to the shelf edge. So this has implications for the morphology of the shelf, but also the slope and the deep sea. And it also has an influence on the surface sediment distribution, and it has an influence on the modern ocean circulation in this area. And you can see that at this time, we think that the ice was around the coastline as indicated here, and then the ice started to retreat into the fjord. And we think that the present position of the ice was reached in the early Holocene, 7,000 to 8,000 years ago. So to conclude, has the northeastern sector of the Greenland ice sheet always been of the same size as today? No, we think the answer is no. It grew to reach all the way to the shelf break during the last glacial maximum. I would also say that right now much less is known on why this is and what is the driving of this evolution, but we seem to find that it reached the present position sometime in the early Holocene, which is roughly 8,000 to 9,000 years ago, and this corresponds to a period in northeast Greenland which is already known, and it's called the Holocene thermal maximum. And we know from the literature that at this time the mean July temperature in the area was probably 2 to 3 degrees higher than today. And then there are some speculations that the driving of the deglaciation of the shelf is related to onset of ocean warming, but that also atmospheric warming come in and influence the deglaciation of the fjord, partly at least because of these very pronounced sills that doesn't really allow for warm water to enter at least into some of the fjords in northeast Greenland. Thank you very much.
Thank you very much. Was indeed quite a different topic after
Yes.
the previous ones, but very interesting. Are there any questions from the audience? Yeah, Philip in the back.
Thank you for this very interesting talk. I was wondering, are there, you showed in the past that there are certain stop points, right, for the glaciers because there's some topographic feature or where they stop. And then I presume once they go beyond that point, then you can have actually quite some rapid retreat with warming. And whether there's some indications of the current position of the Greenlandic ice sheet where you think that could be soon reaching a tipping point where that you get into a much more faster retreating scenario based on where the ice sheet is sitting now in the area you are studying.
Yes, I think my response would be that we know that in some fjords the ice is marine based. In other fjords it has receded onshore, and in the fjords where it's still into the water, there is a potential for a rapid retreat, but we don't really know the bathymetry in very detail in most of these fjords, so it's a bit difficult to say, but I know there are other studies where they have demonstrated that this may be the case. Yes.
Thanks, very nice talk. I was wondering, you mentioned that these ridges that Philip also mentioned are at the seafloor, but you don't see them on land. That seems odd. Any guesses?
It somehow it must be because the onshore ice was not behaving or responding the same way as the ice in the fjord. It could imply that the ice in the fjord is connected to the Greenland ice sheet itself, while in the onshore areas we have more local ice caps that doesn't really reflect or respond the same way. We see that there are areas today where there are local ice caps that seem to react differently, but we need to look into this in more detail to learn more on this. I guess it's lunch.
I guess it's lunch.
Yeah.
And we're ahead of time.
Okay, very good.
Thanks to all the speakers for staying on time. And I'd like to thank also the conveners, all co-conveners and chairs of the session yesterday, Sebastian Gerland, and this morning Agneta Fransson. And I hope everyone had a good time learning new things and got inspired by all the different talks. And hopefully you take your time still to discuss things together and interact. Thanks a lot and enjoy the rest of the Arctic Frontiers. Tack.